Good evening and welcome to The Sleepy Scientist. This channel is a place to unwind with calm, factual science that helps you relax before sleep. Tonight's video is all about one of the most familiar yet most unusual substances in the universe, water. A simple combination of hydrogen and oxygen that somehow makes oceans, clouds, rivers and every living thing possible. Before we start, I'd love to know where you're watching from and your local time. I really love seeing how far spread these videos reach. If you enjoy this kind of relaxing science, please give the video a like and consider subscribing. To everyone who's already subscribed, thank you. Your support really means a lot. And if you'd like to know when the next video goes live, you can click the notification bell so you don't miss it. I hope this video doesn't end up being too interesting and keep you awake. But if it does, at least you'll learn a few surprising things about water before you drift off. So, how did something as simple as two tiny atoms and one larger one come to shape every landscape, every life, and maybe even other worlds beyond our own? Water is everywhere. In the air, in your glass, in the blood that keeps you alive. It's so ordinary that most people never stop to think how strange it really is. For such a simple molecule, it breaks almost every rule in chemistry. It expands when it freezes, clings to itself, dissolves almost everything else, and stores enormous amounts of heat. Without those quirks, Earth would be an empty rock. In this video, we'll take a calm, detailed look at water's full story, from its creation in the hearts of stars to the moment it fell as rain on a young Earth. We'll see why its shape gives it such unusual powers, how it built the rivers and glaciers that shaped our world, and why every cell in your body depends on it. This won't be a lecture or a list of facts, just a slow journey through one of nature's most fascinating puzzles. So get comfortable, let your mind settle, and think about this. Long before there were oceans or clouds, before Earth itself existed, where did the very first drop of water come from? More than 13 billion years ago, the universe was young, hot, and mostly empty. Out of that vast, glowing beginning came the simplest element of all, hydrogen. These were the first atoms to form after the Big Bang, single protons with a light electron circling them, drifting through the cooling darkness. For a long time, hydrogen was almost all there was. No stars, no planets, no chemistry as we know it. Just a silent sea of invisible gas waiting for gravity to do something interesting. When the first stars finally ignited, they began to change everything. Inside their cores, hydrogen atoms were crushed and fused into helium, releasing light that filled the early cosmos. Over time, as these stars aged and died, their furnaces started building heavier elements. Oxygen, the other half of the recipe for water, was one of them. It didn't exist until stars made it, and when those stars exploded as supernovae, they scattered their oxygen into space like cosmic confetti. Each blast seeded the universe with the raw ingredients for future chemistry, including the first possible droplets of water. In the quiet clouds that followed, the real story began. Not with oceans or storms, but with individual molecules finding each other in the dark. Within these cold molecular clouds, the temperature could drop to only a few dozen degrees above absolute zero. Here, atoms crept together slowly, bumping into dust grains and other atoms. Hydrogen, being plentiful and restless, often found itself in triads, tiny clusters of 3 atoms known as H3+. These molecular ions were like matchmakers of the universe, transferring protons and sparking reactions wherever they went. When hydrogen ions met free oxygen atoms or simple oxygen molecules, they formed hydroxyl radicals, short-lived combinations of one oxygen and one hydrogen atom. Those radicals didn't last long before latching onto another hydrogen, and just like that, the first molecules of water appeared. They were fragile, fleeting things, sometimes destroyed by radiation, sometimes frozen onto dust grains, but they were real. The same chemistry that happens in interstellar space today was already underway more than 12 billion years ago. Over millions of years, these dust grains coated with icy mantles clumped together under gravity, forming denser and denser regions that would eventually collapse into new stars. Around each forming star spun a thin disk of gas and dust, a kind of cosmic workshop where the elements could mix and react. In those protoplanetary disks, water existed in both vapor and ice form, creating a subtle boundary scientists now call the snow line. Inside that line, close to the newborn star, it was too warm for ice to survive. Beyond it, temperatures dropped low enough for water to freeze onto grains. Those frozen particles became the building blocks for comets, asteroids, and eventually the icy outer planets. Even at this early stage, water was everywhere, a quiet passenger on the long road to planet formation. When these icy bodies collided and merged, they carried their stored water with them, embedding it into larger worlds. Some of that water evaporated into vapor, some stayed locked in minerals deep underground. The chemistry that began in starlit clouds was now shaping solid ground. When the Earth formed about 4.5 billion years ago, it wasn't the blue world we know today. It was a violent molten sphere under constant bombardment from leftover debris. For a long time, the planet's surface was too hot for liquid water to exist. Any that tried to settle would have boiled away instantly. But as the crust thickened and volcanic activity began to release gases, the early atmosphere slowly filled with steam, carbon dioxide, and nitrogen. Water was trapped inside the rocks of the mantle, and it escaped through volcanic vents and cracks, adding to the growing blanket of vapor above. At the same time, countless comets and water-rich asteroids struck the surface. Each impact delivered more frozen cargo, possibly enough to fill the young oceans many times over. Scientists still debate the exact proportions, whether most of our water came from inside the planet or from space, but the evidence suggests a mixture of both. One clue lies in the ratio of deuterium, a heavy isotope of hydrogen, to normal hydrogen. This deuterium to hydrogen ratio acts like a chemical fingerprint. The ratio found in Earth's oceans closely matches that of certain types of asteroids, suggesting that much of our water may have arrived as rock-bound ice rather than cometary frost. Once the planet cooled enough, the change was almost instant. Clouds thickened, and for the first time rain began to fall. Imagine the sound of it. Drops hissing on hot rock, steam rising from a scorched surface, rivers forming where moments before there had been only fire. It might have rained for centuries without pause, water condensing from the sky and returning as vapor again and again, until the surface was finally cool enough to let the first pools remain. Those pools merged into basins, and the basins deepened into oceans. Steam that had once filled the air condensed into seas that now covered most of the planet. The Earth's face began to glisten for the first time, reflecting starlight and the pale glow of a newborn sun. In a sense, the planet found its shimmer, the thin, shining film of liquid that would one day cradle life. By the time that first sunlight scattered through the atmosphere, Earth's water had already travelled an extraordinary journey. From hydrogen created in the first seconds of the universe, to oxygen forged in the hearts of dying stars, to molecules assembled in dark clouds, and finally to the oceans that lap against our shores today. Every glass of water, every raindrop and snowflake carries atoms that were once part of ancient stars. So the next time you see rain streaking down a window, it's worth remembering that it began billions of years ago in a place without light or warmth. That what you're seeing is the universe itself, condensed into something you can hold. Somewhere deep in the past, a single droplet met the surface of a young Earth for the very first time. It struck hot rock, hissed into steam, and vanished. But in that brief moment, the planet began to cool, and the story of everything that followed quietly began. If you could shrink yourself down to the size of an atom and look at a molecule of water up close, you might be surprised by its shape. It's not symmetrical, not neatly balanced, and certainly not what most people imagine when they think of something so ordinary. Each water molecule is made of one oxygen atom joined to two hydrogens, but instead of sitting in a straight line, the hydrogens bend away from each other, forming an angle of about 104.5 degrees. It's a small detail, but this bent geometry is the reason water behaves like nothing else in the universe. Oxygen is the heavyweight in this trio. It has 8 protons in its nucleus, which gives it a stronger pull on electrons than the lightweight hydrogen atoms beside it. When they form bonds, oxygen doesn't share equally. It hogs the electrons just a little, creating an uneven spread of charge. The oxygen end becomes slightly negative, and the hydrogens become slightly positive. Scientists write this as delta negative on the oxygen and delta positive on the hydrogens. That unevenness makes water a polar molecule, one with a positive side and a negative side, like a microscopic magnet. This polarity might sound like a technical curiosity, but it's the foundation for almost every one of water's strange tricks. Because each molecule has 2 tiny positive tips and 1 negative side, it can attract others in every direction. Opposite charges pull together, and in liquid water, these attractions form and break billions of times every second. It's this constant dance of weak electrical bonds that makes water so cohesive, meaning it tends to stick to itself. If the molecule were perfectly straight and symmetrical, those charges would cancel out, and the substance we know as water would lose most of its personality. Water's dipole moment, a measure of how unevenly the charge is distributed, means it also reacts dramatically to electric fields. In strong fields, water molecules twist and align like compass needles, their positive sides turning toward the negative pole and vice versa. This behavior helps explain why water is such a powerful solvent, and why it can interact so readily with ions and charged particles. Even in an ordinary glass of water, the molecules are constantly orienting, spinning and flipping in response to subtle fields created by dissolved salts and minerals. Polarity also explains something you can actually see. When you place a small droplet of water on a clean surface, it doesn't flatten completely. It forms a bead. That little dome shape is the visible signature of cohesion, the inward pull of water molecules clinging to each other more strongly than they cling to the air. The surface acts like a stretched elastic film, giving rise to what we call surface tension. It's why a water strider can skate across a pond without sinking, and why a carefully placed paper clip can float on water despite being made of metal. At a molecular level, each surface molecule feels a stronger pull toward its neighbours below than toward the empty air above, creating a tight, self-supporting skin. But water isn't just cohesive, it's also adhesive, meaning it's drawn to other materials as well. When a droplet lands on something like glass, the positive hydrogen ends are attracted to the negatively charged oxygen atoms in the glass surface. The result is a subtle competition between cohesion and adhesion. If cohesion wins, the water forms beads that sit high and round like on wax leaves. If adhesion wins, the water spreads out in a thin film, clinging tightly to the surface. You can see this tug-of-war at work every time rain lands on a car bonnet or slides down a window pane. This delicate balance also creates one of water's most useful behaviours, capillary action. In narrow spaces, like the thin tubes inside plants, adhesion pulls water upward along the walls, while cohesion keeps the column of liquid connected. Together, they allow water to climb against gravity, feeding leaves that may sit tens of meters above the ground. The same process lets paper towels soak up spills or draws ink through the nib of a pen. It's one of those quiet physical miracles that seems obvious until you think about what's really happening. Liquid climbing on its own, powered only by the geometry of its molecules. You can see similar effects almost anywhere if you look closely enough. When water clings to the side of a glass, it forms a small upward curve called a meniscus. In a test tube, this meniscus is concave. The edges rise slightly higher than the centre because the water sticks to the glass walls. Mercury, by contrast, forms a convex meniscus that bulges upward because its atoms prefer each other's company to the surface they sit on. In something as simple as that curve, you can see the entire philosophy of water, a constant negotiation between attraction, balance, and movement. If you were to compare a droplet of water on different materials, you'd see how the shape changes with the strength of adhesion. On wax or oily surfaces, the droplet stays almost perfectly spherical, as if the molecules are huddling together to avoid contact. On glass or fabric, it flattens out, spreading wide as the hydrogens reach toward oxygen atoms in the material below. And on the delicate surface of a leaf, you get a mix of both. A round droplet that sticks firmly enough to stay in place yet rolls away when the leaf trembles. Each shape, each curve, is a fingerprint of molecular geometry made visible at human scale. This same structure also helps explain why water interacts so readily with ions, charged particles dissolved in solution. This slightly positive hydrogens surround negatively charged ions like chloride, while the slightly negative oxygen end points toward positive ions like sodium. The result is a kind of microscopic embrace. Each ion becomes wrapped in a shell of oriented water molecules. This process, called hydration, is what allows salts to dissolve and biological systems to function. Without the bent polar shape of water, those ions would stay clumped together, and most of chemistry, from digestion to photosynthesis, simply wouldn't work. Even the smooth surfaces we take for granted depend on this geometry. The thin film of water that coats everything from soil particles to skin cells acts as a lubricant because of those polar attractions. Molecules slide over one another easily but never quite let go, which is why water can feel both slippery and sticky depending on the surface. That same behaviour helps regulate friction inside living organisms, allowing cells to move and muscles to glide. All of this stems from the simple fact that water's electrons don't sit neatly in the middle. Its lopsided design gives it direction, character, and the ability to form fleeting connections that hold entire systems together. Every droplet that hangs from a leaf tip, every bead that rolls across wax, every tiny ripple that breaks and reforms on a pond, all of it happens because of that small, persistent angle of 104.5 degrees. It's easy to overlook just how strange that is. Many molecules around water's size are gases at room temperature: ammonia, methane, hydrogen sulfide. But water's polarity and its network of bonds hold it together as a liquid. Its shape lets it defy the trends that govern most other substances. Without that asymmetry, there would be no cohesion, no surface tension, no rivers or cells or clouds. When you next see a drop of water slide down a window or balance on a leaf, you're really watching billions of polar molecules in perfect coordination, each one tiny and bent, yet all of them working together to create something smooth, continuous, and alive. From the smallest bead on glass to the largest ocean wave, every curve begins with that same subtle angle, the crooked geometry that made the world fluid. If water's shape gives it personality, hydrogen bonds give it structure, an invisible framework that turns chaos into coherence. They are delicate connections, but without them, liquid water simply wouldn't exist. A hydrogen bond forms when the slightly positive hydrogen atom of one molecule is attracted to the slightly negative oxygen atom of another. It isn't a full chemical bond, more a fleeting attraction, electrostatic, directional and temporary, but billions of these brief connections give water its strength. Inside every droplet, this network is alive with motion. Each water molecule can form up to 4 hydrogen bonds at once, but they don't last. In less than a trillionth of a second, one breaks and another forms elsewhere. The result is a constantly shifting pattern of molecular connections, a fluid architecture that rearranges itself billions of times a second. Scientists sometimes call it a liquid with a memory for order. It remembers how to be structured, even as it melts, ripples and flows. That endless motion gives water its texture. Smooth, continuous, but never static. Compared with most small molecules, water flows oddly slowly. The same bonds that link its molecules also hold them back, adding a quiet viscosity. They resist being pulled apart yet yield just enough to move gracefully. This is why water pours with such even rhythm. It stretches without snapping, flexes without scattering into chaos. Hydrogen bonds are the quiet reason a pond can carry a walking insect, or why a leaf holds a perfect droplet after rain. At the liquid surface, molecules have neighbours beside them, but none above, so their bonds pull inward and sideways, tightening the layer into a thin, elastic skin. Surface tension, born from those bonds, gives water its distinctive resilience. To a water strider, that skin might as well be glass. Its legs dent the surface, dimpling the hydrogen-bonded layer without breaking it. From above, the insect's footprints are tiny ovals of tension, ripples in a field of invisible energy. Beneath that same principle lies the difference between a surface that beads with moisture and one that absorbs it. When water meets glass, the molecules find plenty of sites to bond with. The oxygen atoms of the glass attract the hydrogens of the water, spreading the droplet thin. On wax or oil, there's nothing to grab, so the water retreats into itself, forming neat spheres. Cohesion keeps the droplet intact. Adhesion determines where it stays. Together they make the world's smallest tug-of-war, shaping how rain gathers, drips and slides. In narrow spaces, hydrogen bonds pull off an even stranger trick: capillary rise. When a thin tube touches water, the molecules at the edge cling to the walls while still holding tightly to one another. That combined pull draws the entire column upward, seemingly against gravity. In trees, this effect is magnified through millions of tiny tubes in the xylem. As water evaporates from the leaves, more is drawn up to replace it, rising metre by metre through nothing more than molecular cooperation. No engines, no pumps, just hydrogen bonds and the quiet persistence of physics. Those same bonds also turn water into a remarkable caretaker for other substances. When an ionic compound like salt dissolves, its charged particles are immediately surrounded by clouds of water molecules. The positive hydrogens turn toward chloride ions, the negative oxygens face sodium. These hydration shells act like bodyguards, preventing the ions from reuniting. Without them, salt would stay solid, and most biological chemistry would come to a standstill. The same process happens inside you. Every ion in your bloodstream, sodium, potassium, calcium, is wrapped in a halo of water molecules, each held in place by those fleeting bonds. They keep nutrients moving, maintain the delicate balance of your cells, and help transmit electrical signals that let your muscles contract and your heart beat. Water isn't just a solvent here. It's an active participant in the choreography of life. Even in the stillness of a glass, water never truly rests. At any moment, countless bonds are forming and breaking, creating tiny fluctuations that ripple through the liquid. These rearrangements scatter light, giving clean water its faint blue tint. Under the right conditions, the same microstructure creates shimmering thin films, the kind you see on bubbles or the surface of freshly poured water. What looks calm from afar is actually an unending rearrangement at the molecular scale. The beauty of hydrogen bonding is in its impermanence. Each bond is weaker than a typical covalent bond by a factor of 20, but that weakness is exactly what allows flexibility. Ice owes its structure to hydrogen bonds frozen in place, but liquid water owes its fluidity to their transience. They hold together just long enough to cooperate, then let go to reform elsewhere. This balance between order and chaos gives water its dual identity, stable yet adaptable, strong yet endlessly soft. Nature uses this property in extraordinary ways. Inside living cells, hydrogen bonds in and around water guide the folding of proteins into the precise shapes needed for life. They stabilize DNA, holding its two strands together until it's time to separate and copy genetic information. Even enzymes rely on water's hydrogen bonding ability to position molecules perfectly before a reaction. Every beat of your heart, every flicker of thought depends on these quiet electrostatic whispers linking molecule to molecule. Beyond biology, the same physics shapes the natural world. The curve of a droplet on a leaf, the shimmer of morning dew, the gentle pull of sap up a redwood. All are manifestations of hydrogen bonding in action. It's a force so small that it can't be seen directly, yet so universal that it dictates the behavior of oceans and clouds alike. The wonder lies in how temporary these bonds are. In less than a blink of an eye, the arrangement of molecules in a lake, a cloud, or even a teacup has completely changed, yet the water's identity stays the same. It's an ever-renewing network that never loses its coherence. Each molecule plays its part for a moment, then hands the connection on to another, keeping the chain unbroken. Every droplet, every ripple, every patch of mist is made of these fleeting bridges. They are the quiet architect of liquid life, invisible, transient, and endlessly rebuilding. Without them, water would spill apart into vapor or freeze into brittleness. With them, it flows, clings, climbs, and carries the chemistry of the world. Hydrogen bonds are proof that strength doesn't always come from permanence. Sometimes it comes from the ability to change quickly, to connect and release in perfect rhythm. They are the reason a puddle reflects the sky, a river holds its shape, and a living cell can exist at all. Tiny, momentary threads holding together the fabric of the liquid world. When most substances freeze, they shrink and sink. Their molecules slow down, move closer together, and pack into denser, heavier forms. Water, of course, does the opposite. It refuses to follow the rules. When it freezes, it expands, becoming lighter, larger, and able to float upon itself. It's one of the strangest quirks in chemistry, and one of the most important reasons life on Earth exists at all. The reason lies in the structure water adopts as it turns to ice. In its liquid form, the molecules are constantly jostling and rearranging, their hydrogen bonds forming and breaking 1 trillion times a second. But as the temperature drops, that restless movement slows. The molecules start to settle into a fixed pattern, aligning themselves through hydrogen bonds into a precise geometry, a hexagonal crystal lattice. This lattice looks like a honeycomb made of molecules, neat rings of 6, connected by delicate bridges of hydrogen bonds. It's beautifully ordered but surprisingly spacious. Each molecule holds its neighbours at arm's length, leaving tiny pockets of empty space within the pattern. This open framework makes ice less dense than liquid water. Instead of packing tightly, the molecules spread apart just enough to give solid water more volume for the same mass, which is why it floats. If you've ever watched ice cubes bob in a glass or seen a frozen pond with liquid water beneath it, you're witnessing this quiet defiance of physics. In almost every other material, the solid phase sinks. But because ice is less dense, it forms a floating lid instead. That simple fact has saved countless ecosystems from freezing solid. The magic doesn't stop at the surface. Liquid water reaches its maximum density at around 4 degrees Celsius, just a few degrees above freezing. That means when water cools, the densest layer sinks to the bottom, while the lighter, colder layers stay on top. In winter, as the air chills the surface, water near the top cools to 4 degrees and sinks, mixing the lake until the entire volume reaches that temperature. Any further cooling creates water that's less dense, so it stays near the surface, eventually freezing into ice. This layering creates a remarkable refuge. Beneath the ice, the water remains liquid, insulated by the frozen sheet above. Fish and aquatic plants survive the coldest months in this stable environment, safe from the freezing air. Even in the harshest winters, the world under the ice continues quietly, shielded by a crystalline ceiling that lets light through but keeps the warmth in. Without that density anomaly, every pond and lake would freeze solid from the bottom up each year, leaving nothing alive when spring returned. Water's relationship with temperature and pressure is unusually complex, something chemists describe with a phase diagram. In simple terms, it's a map showing which form water takes under different conditions. At low temperatures and low pressures, ice dominates. As temperature rises, it melts into liquid, and at still higher temperatures or lower pressures, it becomes vapor. But ice itself isn't just one kind of solid. Under different combinations of pressure and temperature, it can form at least 19 distinct crystalline structures known as polymorphs. The one we're familiar with, the type that forms snowflakes, frost and frozen lakes, is called Ice 1H for hexagonal. Its molecules are arranged in that open six-sided network we see in snow crystals. Under higher pressures, though, the structure changes dramatically. Ice 2, Ice 3, and beyond all have denser arrangements where molecules are squeezed into tighter patterns. Some of these exotic forms exist naturally deep inside icy moons and planets, where crushing pressure transforms water into something more like rock than crystal. Even on Earth, you can glimpse the influence of ice's expansion in the slow, patient force it exerts on the world around it. When water seeps into cracks in rock and freezes, the growing ice pushes outward. It might only expand by about 9%, but that's enough to wedge stones apart and carve landscapes over millennia. Mountains crumble grain by grain, boulders fracture, and cliffs erode, all because frozen water gently insists on taking up a little extra space. This process, known as freeze-thaw weathering, is one of nature's quiet engines of change. It works in silence season after season, breaking down mountains to make soil and valleys where forests will one day grow. The same expansion also gives rise to frost heave in soil, when moisture trapped underground freezes and swells, lifting the earth and shifting roads, rocks, and roots. It's an inconvenience to engineers, but a gift to ecology. That subtle stirring of the ground mixes minerals, aerates the soil, and prepares it for the next cycle of growth. Ice may seem still, but it never stops reshaping the world. On a smaller scale, the hexagonal symmetry of ice gives snowflakes their iconic beauty. Each crystal begins as a speck of dust or pollen, around which water vapor freezes, forming a six-sided seed. As it tumbles through changing layers of air, the molecule-by-molecule architecture of the lattice builds outward in branching, intricate patterns. No two flakes are truly identical, because the path each one takes through the sky is unique, yet all share the same foundation, the hexagonal bond geometry that water chooses every time it slows and solidifies. In glaciers, the structure becomes a record of history. As snow accumulates and compresses, it traps pockets of air between ice crystals. Over thousands of years, those tiny bubbles become sealed time capsules, Scientists can drill deep into ancient ice sheets and extract cores that preserve samples of the atmosphere from long before humans existed. The faint blue glow of ancient glacier ice isn't just beautiful. It's a window into vanished climates, each bubble a whisper from a colder, quieter past. Even the sound of cracking ice carries traces of its structure. When a frozen lake groans or splits in winter, what you're hearing is the sudden readjustment of millions of crystal bonds. Temperature changes cause the lattice to contract or expand unevenly, creating echoes that travel across the surface. Beneath the noise, hydrogen bonds are stretching and sliding back into alignment, the same network that once floated snowflakes now resonating like a frozen drum. For all its apparent fragility, ice is one of the strongest materials in nature. A block of pure, cold ice can bear immense weight before breaking, thanks to the strength of its hydrogen-bonded lattice. Yet it remains light enough to drift, forming an ever-shifting balance between rigidity and buoyancy. It's a substance that manages to be both solid and gentle, a paradox of physics shaped entirely by geometry. Water's decision to expand when it freezes might seem like a minor technical detail, but without it, Earth would be unrecognizable. Rivers would freeze from the bottom up, oceans would become blocks of solid ice, and the seasonal rhythm of life would halt. The same delicate structure that traps air in glaciers also traps warmth beneath a winter surface, preserving the live and pulse of the planet. Every frozen pond, every icicle, every drifting flow is built from that same repeating hexagonal pattern, a molecular architecture that stretches across continents. In the depths of ancient ice, the air bubbles glint faintly blue, suspended in perfect stillness. Each one holds a trace of breath from an age long gone, a record of warmth and cold preserved by the quiet generosity of water's most improbable trick, a solid that floats. Water doesn't just quench thirst or shape landscapes, it quietly governs the temperature of almost everything around us. It's the reason coastal towns feel mild while deserts swing from blistering heat to freezing nights. It's why your body can stay near the same temperature whether you're sitting in snow or sunlight. Among all known liquids, water is one of the best at storing and releasing heat, making it the planet's thermal guardian. To understand why, it helps to think about how hard it is to warm water up. Every substance has what's called a specific heat capacity, the amount of energy required to raise its temperature. For water, that number is unusually high. It takes more heat to warm a cup of water by 1 degree than it does for almost any other common material. The reason lies in the same invisible hydrogen bonds that hold its molecules together. Before the temperature can rise, much of the added energy goes into bending, stretching, and breaking those tiny bonds. Only when enough are disrupted do the molecules begin to move faster, and the water actually gets warmer. This is why a beach can feel scorching while the sea beside it remains comfortably cool. Sand heats quickly because it stores little energy. Water heats slowly because it absorbs so much. And at night, when the air cools, the process reverses. The land gives up its heat rapidly, but the ocean releases it gradually, keeping coastal air mild long after sunset. It's a quiet exchange that shapes weather, winds, and even the survival of entire ecosystems. The same property works closer to home. Imagine stirring a pot of soup on the stove. The longer it simmers, the more evenly its temperature spreads. That's because water distributes heat remarkably well. The molecules are in constant motion, bumping into each other and sharing energy evenly throughout the liquid. This efficient balancing act is what prevents most of your dinner from burning while a small corner boils over. In a way, water behaves like a natural thermostat. It resists sudden changes and spreads warmth wherever it flows. But there's more to water's relationship with heat than just how much it can hold. There are also the hidden thresholds called latent heats, the energy needed to change water's state without changing its temperature. When ice melts, for example, it absorbs a large amount of heat simply to loosen its rigid lattice. Yet during the entire process, the temperature remains at 0 degrees Celsius until every last crystal has turned liquid. That absorbed energy is stored invisibly in the water itself, ready to be released again when it freezes. An even greater amount of energy is required to turn liquid water into vapor. To evaporate, each molecule must break free from its neighbors completely. The hydrogen bonds that make water cohesive now become obstacles, demanding energy to escape. The result is that water can absorb tremendous amounts of heat as it evaporates, and this is precisely why sweating cools the human body. As sweat evaporates from the skin, it draws away heat energy, leaving the surface cooler. It's the same process that keeps plants from overheating when moisture evaporates from their leaves. The flip side happens during condensation. When water vapor in the air cools and returns to liquid form, on a window, a leaf, or your skin after a hot shower, it releases the energy it once borrowed. That gentle warmth you feel from mist or a steamy bathroom isn't your imagination. It's latent heat being given back. Nature uses this trade-off constantly. Clouds form when warm, moist air rises and cools, causing water vapor to condense and release heat. This energy powers storms, fuels rainfall, and drives much of the planet's weather. On a smaller scale, we use the same principle every day without thinking about it. When you boil water in a kettle, the energy from the stove doesn't just raise the temperature, it also goes into pushing molecules apart until they burst free as steam. That's why the temperature plateaus once boiling begins. All the incoming heat is being converted into the energy of evaporation. The cloud rising from the spout carries away vast amounts of stored warmth, invisible until it touches something cooler and turns back into droplets. This interplay of heating, cooling, and transformation gives water its deep connection to comfort. It's why a warm bath feels steady rather than scalding. The water's high specific heat makes it resistant to sharp temperature shifts. It's why a cup of tea stays warm long after it's poured, slowly releasing the energy it's absorbed. And it's why walking through coastal fog can feel strangely mild, the air wrapped in moisture that buffers the extremes. Water's control over temperature also shapes entire climates. The world's oceans act as immense heat banks, absorbing warmth during the day and releasing it during the night or through colder seasons. This moderation keeps temperatures in check, preventing the wild swings that plague drier landscapes. Even the gentle breeze that moves inland on summer afternoons, the sea breeze, owes its existence to the difference in how land and sea store heat. As the land warms faster, air rises and cooler air from over the ocean rushes in to take its place. The planet's weather, at its core, is an elaborate conversation between sunlight, air, and water's remarkable capacity for heat. Hot springs, geysers, and volcanic pools offer another glimpse of water's thermal nature. Beneath the ground, heated water can hold energy for years, carrying warmth up from deep rocks and releasing it slowly at the surface. Ancient civilizations built entire cultures around these natural baths, long before they understood the physics behind them. The same phenomenon that calms the human body also stabilizes the planet itself, a shared rhythm of heating, holding, and releasing energy. Water's thermal behavior is also essential in cooking. Steaming vegetables, poaching eggs, brewing coffee, each relies on precise control of temperature. Steam, though invisible when it first leaves the pot, is one of the most efficient carriers of heat known. When it condenses on cooler food, it releases its hidden energy in an instant, cooking evenly without scorching. That's the same reason steam burns are more severe than burns from boiling water. The vapor gives back its latent heat all at once. Even everyday sights reveal this quiet physics. When you see a bathroom mirror fog after a shower, what you're looking at is the moment vapor surrenders its stored energy and turns back into liquid. Each tiny droplet forming on the glass has just given off a microscopic burst of warmth. A kettle's plume carries away energy from the water below, rising, cooling, and vanishing into the air. In a sense, every puff of steam and every bead of condensation is part of a slow exchange, a whisper of heat moving from one place to another. This ability to store and release warmth with patience and precision makes water one of the universe's most effective mediators of temperature. It smooths the peaks and valleys of heat, spreads energy evenly, and protects life from extremes. Without it, Earth would swing wildly between burning days and frozen nights. With it, the planet stays in balance, buffered by trillions of tons of calm, steady liquid. In the end, it's not just numbers or equations that make water remarkable, it's the way we experience it. The warmth of a cup between your hands, the mist on a mirror, the soft exhale of a kettle. Each is a small lesson in the physics of comfort. Water takes heat, holds it, moves it, and gives it back gently, like a caretaker tending an endless fire. It's the reason your breath fogs on a cold morning and the air feels soft after rain. A quiet reminder that behind every calm moment lies an ocean of energy, waiting to rise and fall in perfect balance. Water is often called the universal solvent, and for good reason. Few substances can resist its ability to pull things apart at the molecular level. Salt, sugar, gases, minerals, all find themselves undone and rearranged by this simple liquid. The secret lies in water's polarity. Each molecule carries a slightly negative charge on its oxygen end and a slightly positive charge on its two hydrogens, creating a tiny electrical imbalance that makes it irresistibly interactive. When you drop ordinary table salt into water, that polarity goes to work instantly. Salt is made of sodium and chloride ions held together by strong electrostatic forces. In solid form, they cling to each other tightly, forming crystals. But when they meet water, something remarkable happens. The positive hydrogens in the water are attracted to the negatively charged chloride ions, while the negative oxygen ends face the positively charged sodium ions. One by one, the water molecules surround the ions, forming little cages known as hydration shells. Each ion becomes wrapped in layers of water, its former bonds to the crystal severed. The salt dissolves, not by vanishing, but by being embraced, separated and stabilized in a new kind of order. This same process explains why sugar melts away so easily in your tea, while oil stubbornly floats on top. Sugar molecules, though large, are studded with oxygen and hydrogen atoms that can form hydrogen bonds with water. Oil, on the other hand, is made mostly of long chains of carbon and hydrogen, which share electrons evenly and offer no charges for water to grab onto. To water molecules, oil is like a guest at a dance who refuses to hold hands. The two simply part ways, the water gathering with its own kind and the oil forming droplets above it. That refusal to mix gives rise to one of chemistry's quiet wonders, micelles. When certain molecules have both a water-loving end and a water-fearing end, such as soap, they arrange themselves into tiny spheres. The hydrophobic tails tuck inside, safe from water, while the hydrophilic heads face outward. These micelles trap oils and dirt within, allowing them to be rinsed away. It's one of nature's simplest and most elegant cleaning tricks, born entirely from the way water interacts with charge. But water's dissolving talents go even deeper. Even pure water isn't truly empty. Its own molecules occasionally break apart in a delicate balance known as self-ionization. At any given moment, a few molecules separate into a positively charged hydrogen ion, which in reality is a bare proton, and a negatively charged hydroxide ion. These ions exist in equal amounts, maintaining water's neutrality. The product of their concentrations is called Kw, the ionization constant of water. It's small, only about 10 to the power of -14 at room temperature, but it underpins the entire concept of pH. pH, short for potential of hydrogen, measures the concentration of hydrogen ions in a solution. A neutral solution, like pure water, has a pH of 7 because the hydrogen and hydroxide ions are perfectly balanced. When acids dissolve in water, they donate extra hydrogen ions, lowering the pH. When bases dissolve, they mop up those ions, raising it. This simple equilibrium governs the chemistry of oceans, blood, and soil alike. And though we often think of neutral water as inert, it's actually alive with tiny fluctuations. A quiet equilibrium that never stops shifting. Water also dissolves gases, a feature that keeps the planet breathing. Oxygen and carbon dioxide both slip into water molecules through weak interactions. Fish depend on dissolved oxygen, and plants in the sea release it again during photosynthesis. Temperature plays a crucial role. Cold water holds more gas than warm water. That's why mountain streams are so lively with bubbles, and why warm lakes can suffocate fish during heat waves. Every change in temperature alters the delicate balance between water and the air above it. Carbon dioxide is especially important. When it dissolves in water, it reacts to form carbonic acid, a mild but influential substance. This interaction links the chemistry of the atmosphere with that of the oceans. It's part of a global balancing act, carbon moving quietly between air, water, and rock. Without it, the planet's climate and geology would evolve in very different ways. Geology offers some of the most striking demonstrations of water's dissolving power. When rainwater, slightly enriched with carbon dioxide, seeps into the ground, it becomes a gentle acid capable of slowly eating away limestone. Over centuries, that process carves vast underground caverns and tunnels. Stalactites and stalagmites grow drop by drop as dissolved minerals are redeposited when the water evaporates. Each icicle-shaped formation is a frozen record of chemistry in motion. Water dissolving, carrying, and rebuilding stone with infinite patience. Mineral springs provide another example. As groundwater travels through layers of rock, it picks up trace elements: calcium, magnesium, iron, until it emerges at the surface, enriched and distinct in taste. Some waters bubble naturally with dissolved carbon dioxide, forming effervescent springs prized since ancient times. Civilizations have long treated these mineral waters as curative, not just for their warmth, but for their complex chemistry. What people once described as life in the water is, in scientific terms, the quiet work of dissolution and equilibrium. Even something as simple as taste reflects the chemistry of water. The purest distilled water, stripped of all ions and minerals, can taste strangely flat, almost empty. It quenches thirst but lacks character. Mineral-rich waters, by contrast, carry subtle notes depending on their contents: a hint of sweetness from calcium, a metallic edge from iron, a smooth softness from bicarbonate. Some cultures have turned this into ritual, celebrating the local differences as though water itself were a kind of wine. Each spring and river tells a geological story through its flavour. This variety also explains the difference in mouthfeel between different waters. Hard water, rich in calcium and magnesium, can feel heavier or slightly chalky, while soft water glides easily across the tongue. None of these traits make one kind better than another. They simply reveal water's astonishing sensitivity to the materials it encounters. Every pipe, rock, or cloud leaves its signature on the liquid that passes through. From a scientific standpoint, water's universality as a solvent lies in its ability to balance opposites. It can pull ionic compounds apart yet stabilize them in solution. It can host acids and bases at the same time, maintaining a dynamic equilibrium. It can dissolve gases, shape landscapes, and carry minerals across continents, all because of its simple polarity. Other liquids dissolve some things well, but few dissolve so much, so gently and so dependably. It's worth pausing to consider how this behaviour touches daily life. From the fizz of a carbonated drink to the sparkle of a stalactite, from a tea steeping in a cup to the formation of coral reefs, all depend on the same molecular skill. Water takes what is solid, separates it without violence, and makes it part of something larger. Perhaps that's what gives it its quiet elegance. It's not a force that smashes or burns, it persuades. It pulls molecules apart with patience and holds them safely within its embrace. In every glass, every ocean wave, and every drop of rain, that same balance plays out. Polarity meeting charge, chemistry meeting calm. Water dissolves the world not by destroying it, but by connecting it, molecule to molecule, until everything is part of a single flowing whole. Every landscape on Earth has been touched, shaped, or rewritten by water in motion. A single drop of rain may seem harmless, but multiplied across the sweep of a storm it becomes a sculptor. It digs, smooths, and carries away. Over centuries, rivers and rain have carved mountains into valleys, ground rock into sand, and drawn intricate lines across continents. The Earth's surface, in many ways, is water's patient artwork. The story begins with rain. When clouds finally release their burden, each droplet falls with the energy of its descent, striking soil, rock, or leaf. Some soak in, some evaporate, and some begin to flow. At first, this movement is barely noticeable. A thin sheet of water spreading across the surface, following tiny irregularities in the ground. This sheet flow gathers strength as it moves downhill, and soon the water begins to organize itself. Small channels form, called rills. These merge into larger grooves known as gullies, which grow into the earliest forms of streams. As the water gathers, it carries with it small fragments of the land, grains of sand, bits of clay, specks of organic matter. Each raindrop that splashes against the ground loosens another particle, setting it free to travel. The steeper the slope, the faster the flow, and the more material it can carry. The process is simple but relentless. A hillside after a storm may look unchanged, but on the smaller scale it's been reshaped. Soil shifted, rocks smoothed, roots exposed. Over time, as streams merge and grow, they become rivers, the most expressive sculptors of all. Rivers don't carve in straight lines, they meander. Look at any aerial photograph of a floodplain, and you'll see the gentle curves, the loops and bends that mark a river's restless path. These meanders are not random. They're the natural outcome of flowing water meeting friction. Where the current moves fastest, on the outer edge of a bend, it erodes the bank, cutting deeper into the land. On the inner edge, where the current slows, sediments settle out and form sandy point bars. The bend grows wider, drifting gradually downstream like a snake through grass. Given enough time, a meander can become so exaggerated that the river eventually cuts across its own loop, leaving behind a crescent-shaped lake called an oxbow. These isolated pools are the fingerprints of old rivers, reminders of how the water once turned and twisted before finding a shorter path. Each curve and cut-off tells a story of energy, friction, and balance. Rivers are always negotiating between gravity pulling them forward and the landscape trying to slow them down. The sediments rivers carry are their tools as well as their byproducts. Coarse gravel scrapes at the riverbed, sand scours rock, and silt clouds the water like a painter's wash. But as the current slows, the river changes from sculptor to builder. Where it reaches flat ground, it begins to deposit the load it's carried, layer upon layer of fine material, spread by currents and tides. This is how deltas are born. A delta forms where a river meets a standing body of water, such as a lake or the sea. As the flow slows abruptly, suspended sediments drop out, building up wedge-shaped plains that stretch outward over time. The Nile, the Mississippi, and the Ganges have all built vast fertile deltas this way, landscapes both fragile and rich. Their soils are constantly renewed by fresh deposits, making them ideal for life but vulnerable to change. Alluvial fans follow the same principle but in drier places, where rivers flow from steep valleys onto flat plains. Instead of forming a wedge in water, the sediments spread into a fan shape, glittering with pebbles and sand washed down from the mountains. In both forms, the hand of water is visible, drawing, erasing, and redrawing the land in slow motion. While rivers sculpt mechanically, they also shape the planet chemically. As water moves across rock, it dissolves minerals, carrying away invisible cargo. Carbonate rocks like limestone are especially susceptible. Rainwater, slightly acidic from dissolved carbon dioxide, reacts with calcium carbonate, slowly eating away the stone. Over thousands of years, this process hollows out caverns and sinkholes, leaving behind underground labyrinths of stalactites and stalagmites. Each drop that falls from a cave ceiling contains a trace of the dissolved rock above, which it redeposits as it drips and evaporates. In this way, water can both destroy and create, dissolving mountains while building delicate mineral cathedrals below. The same chemistry continues in every stream. Silicate minerals break down into clays, releasing ions that plants later use as nutrients. Tiny traces of dissolved salts flow to the ocean, where they accumulate over millions of years, giving seawater its familiar brine. A glass of seawater today holds molecules that have been recycled through countless rivers, rains, and rocks, a mineral memory of the continents themselves. Even the colour of a river tells a story of its chemistry. A milky turquoise stream in the Alps owes its hue to rock flower ground fine by glaciers. A reddish-brown current in the tropics carries iron-rich sediments from ancient soils. A green, slow-moving river may be alive with algae nourished by the minerals it transports. The palette of flowing water is as varied as the materials it wears away. For all its strength, water also knows restraint. In some seasons, rivers rest, shrinking to thin threads between exposed stones. In others, they wake violently, swelling with floodwater, spilling across their banks and leaving behind new layers of silt when they retreat. Each flood renews the floodplain, replenishing soil fertility, smoothing the river's curves and reminding everything nearby who truly shapes the land. Civilizations have flourished and fallen by these cycles, timing harvests and rituals to the rhythm of the river's rise and fall. There's a quiet balance in this process: erosion and deposition, loss and renewal. The Himalayas crumble grain by grain, feeding deltas thousands of kilometers away. A particle of dust on a mountain slope may one day settle in an estuary, or drift into the sea to become part of the next generation of rocks. Through it all, water remains the courier, endlessly moving matter from place to place, patient and impartial. On a smaller scale, rain continues the work of shaping and nourishing. Each storm rejuvenates the surface of the land. Raindrops compact soil here, loosen it there, wash nutrients into roots, and carve minute channels that will one day grow into streams. The scent of rain on dry earth, called petrichor, comes from oils and compounds released when drops strike the ground. It's the smell of chemistry and renewal, the planet's quiet sigh of relief. If you listen closely, you can hear the language of rain, a steady patter on leaves, a soft drumming on rooftops, a distant roar as it gathers into runoff. All are voices of the same process. The sound of rainfall is the signature of replenishment, each drop part of an endless cycle of erosion, transport, and rebirth. Rivers and rain have been sculpting Earth for billions of years, wearing down the old and laying the foundations for the new. When the storm ends and the world falls silent again, you can almost feel the surface of the planet exhale. a thin film of water sinking into the soil, a renewed gleam on every stone, the faint hush of movement continuing underground. What began as raindrops becomes rivers, what rivers carve becomes continents, and what they carry away will one day rise again as mountains. The water never stops working, never stops moving, and never forgets the shape of the world it made. High in the world's coldest regions, where snow rarely melts and the air holds more silence than sound, the slowest rivers on Earth begin to take shape. Each winter adds another thin layer of snow, fragile at first, then compacted by the weight of the years above it. What starts as soft crystals soon becomes something denser and more determined. Firn, the halfway state between snow and ice. Grain by grain, air is squeezed out, the crystals fuse together, and over decades the mass transforms into glacial ice. Dense, heavy, and alive with movement. Though it seems frozen and still, a glacier is never truly motionless. It flows, inching forward under its own immense weight. At the surface, brittle ice cracks and folds, but deep below, the pressure turns it plastic, capable of bending and stretching without breaking. This process, called plastic flow, allows glaciers to creep downhill like thick syrup, following valleys carved long ago by water. Beneath the ice, another kind of motion takes place. Basal sliding. Meltwater trapped between rock and ice acts as a lubricant, letting the glacier glide over its bed with quiet persistence. Together, these movements let something seemingly solid behave like a liquid, advancing a few centimeters to several meters each day, depending on slope and temperature. Over centuries, glaciers sculpt entire landscapes. They carve deep U-shaped valleys where once narrow rivers ran. The difference is striking. River valleys tend to form steep-sided V-shapes, but glaciers, with their immense weight, scrape and grind the walls and floor evenly, leaving behind broad troughs that open toward the sea. At the valley heads, glaciers gouge out amphitheatre-like hollows called cirques, the birthplaces of glaciers, where snow first gathers and turns to ice. High ridges between neighbouring glaciers are sharpened into arêtes, and where several cirques meet, their peaks are carved into knife-like spires called horns. The famous Matterhorn in the Alps is one of these, sculpted by ice into its perfect pyramid shape. As glaciers advance, they act like slow-moving bulldozers, pushing rocks and debris before them. When they retreat, they leave behind mounds of this material known as moraines. Some form at the sides, others at the snout, and still others mark ancient stages of retreat, like footprints of the glacier's long journey. Beneath the ice, as the glacier moulds the land, it leaves behind drumlins, elongated hills shaped like teardrops, pointing in the direction of the ice's flow. Each landform tells part of the same quiet story, the relentless patience of frozen movement. Inside a glacier, beauty hides in its colour. Pure glacial ice isn't white, but a deep, luminous blue. The reason lies in the way ice interacts with light. When sunlight enters the ice, the red and yellow wavelengths are absorbed, leaving behind the shorter blue wavelengths that scatter back to our eyes. The thicker the ice, the more pronounced the colour becomes. A thin crust of snow glows pale and milky, but deep crevasses and ice caves shine with an otherworldly turquoise, like frozen oceans turned solid. Those crevasses, long cracks in the glacier's surface, are both dangerous and magnificent. They form where the ice stretches as it moves over uneven ground, opening deep fissures that can reach tens of meters down. From above, they appear as jagged blue scars, tracing the stress lines of the glacier's slow advance. In places where the glacier flows over steep drops or obstacles, the surface fractures into towering blocks called seracs. These frozen pillars can rise taller than buildings, constantly shifting as gravity and meltwater tug at their foundations. Seen in the pale light of dawn, a field of seracs looks like a cathedral built from blue glass, every wall and spire carved by time rather than hand. Beneath the ice, another kind of artistry unfolds. As glaciers grind against bedrock, they act like giant sheets of sandpaper, pulverizing rock into an ultrafine powder known as rock flour. This powder is carried away by meltwater streams, colouring the water an opaque milky turquoise. The famous glacial lakes of the Alps and the Canadian Rockies owe their surreal hues to this mineral dust suspended in their depths. Each summer, as meltwater flows stronger, the lakes brighten. In winter, when the glaciers retreat, they fade to a calmer tone. Nature paints these colours anew each year, one melt season at a time. The erosion beneath glaciers shapes not just valleys, but entire mountain ranges. As the ice grinds forward, it scours away loose rock, smoothing hard surfaces and carving striations that reveal the direction of movement. When the glacier finally melts, it leaves behind a transformed landscape, polished stones that catch the light, boulder-strewn plains, and basins that fill with meltwater to become new lakes. In the quiet aftermath, plants creep back into the soil, and the long cycle of erosion and renewal continues. To human eyes, glaciers may seem eternal, but their lives are measured in slow, deliberate rhythms. They grow in times of heavy snowfall and shrink during warmer periods, advancing and retreating with the patience of ages. Some expand for thousands of years before withdrawing, others surge forward rapidly only to fall still again. Scientists studying ice cores drilled from ancient glaciers can read these movements in the layers, thin bands of compressed snow that preserve tiny bubbles of trapped air. Within them lie records of past atmospheres, volcanic eruptions, and even changes in sunlight from centuries ago. A glacier, in that sense, is not only a sculptor but also an archivist, storing the memory of the world in frozen form. Even the sound of a glacier reveals its hidden vitality. Beneath the apparent stillness, ice groans, pops, and sighs as it shifts and settles. Cracks echo through the valley, followed by silence so complete it seems to hum. Each sound marks a tiny rearrangement, a fracture forming, a serac falling, a hidden stream carving a new tunnel beneath the ice. To stand near one is to feel time stretched thin, seconds marked by the slow pulse of centuries. Every glacier carries its own signature, its flow rate, its debris, its colour, but all share the same patient purpose. They grind mountains down and build valleys up, ferry minerals to the sea, and feed rivers that sustain life far below. They work invisibly, reshaping continents 1 millimetre at a time. At the end of their journey, glaciers return what they borrowed. The ice melts into rivers that sparkle with fine silt, feeding forests and wetlands far downstream. The particles of rock once trapped beneath the ice become the fertile ground for future growth. In this way, the glacier's work never truly ends. It simply changes form, continuing the endless cycle of creation and renewal. If you were to pause in that frozen world, the air sharp, the snow muffled, you might notice the smallest movement, a crack spreading, a low rumble echoing through the valley. In that single sound lies the glacier's heartbeat, measured not in seconds but in centuries. Each shift, each sigh, is part of a story written slowly, patiently, across the face of the earth. The ocean is vast beyond imagination, a single, continuous body that wraps around the world and hides most of its secrets beneath a moving skin of blue. From the shore it looks simple, a sheet of water rising and falling in slow rhythm. But beneath the surface the sea is layered, structured, and alive with invisible motion. The deeper you go, the stranger it becomes. Light fades, temperature drops, and sound begins to travel farther than sight. At the top lies the surface mix layer, stirred constantly by winds, waves, and currents. It's the ocean most people know, warm, sunlit, and full of life. Here, sunlight can penetrate to a depth of about 200 meters, though it weakens with every passing meter. The upper waters are churned and blended daily, making them uniform in temperature and composition. Below that warmth lies a narrow, mysterious boundary called the thermocline. In this zone, temperature plunges rapidly. A few hundred meters can mean a drop of 10 degrees or more. The water above is buoyant and active. Below it, the cold abyss begins. Past the thermocline lies the deep ocean, sometimes called the abyssal plain. Here, light vanishes entirely, and temperatures hover just above freezing. Pressure builds to crushing levels, yet the water moves with astonishing calm, flowing slowly through vast underwater valleys and ridges. It's a realm where light can't reach, but sound can. In fact, sound travels farther and faster underwater than in air. Whales rely on it to communicate across hundreds of kilometers, their calls bending through layers of different density. Submarines use it to map the seafloor, tracing echoes through the dark. Even the faint hum of distant waves can be heard deep below, transformed into soft vibrations that ripple through the deep like the ocean's own whisper. The layering of the sea isn't just a matter of temperature. It's shaped by salinity too. Saltier water is denser than fresh water, and when differences in salt content meet differences in temperature, they create subtle bands of stratification. In polar regions, cold water sinks to great depths, while in the tropics, evaporation leaves surface layers dense and heavy. The ocean is always balancing itself, mixing and separating, endlessly adjusting its density like an enormous breathing organism. These small shifts drive some of the planet's largest currents, linking surface winds to the deep, slow circulation that redistributes heat around the world. Near the surface, this invisible structure becomes visible through motion, waves, swells, and the faint patterns they leave behind. A wave is simply energy moving through water, not the water itself moving forward. The molecules rise and fall in place, tracing circles as the energy passes. Most waves are born far away, stirred by winds over open seas. They travel for thousands of kilometers, organizing themselves into swells, smooth, rolling humps of energy that arrive at distant shores long after the storm that made them has faded. Standing at the edge of the sea, you can feel those swells as a steady rhythm beneath the chaotic splash of smaller waves, the ocean's heartbeat slow and patient. There are also waves hidden below the surface, internal waves that ripple along the boundaries between layers of different density. They can rise hundreds of meters tall, yet remain invisible from above. Satellites sometimes detect their faint signatures, lines and curves where the surface water subtly shifts in color or texture. Beneath the calm, these giant slow waves roll endlessly through the dark, mixing nutrients and shaping the ocean's internal weather. The constant motion doesn't stop with waves. Twice each day, the entire sea responds to a larger rhythm, the tides. These slow surges are caused by the gravitational pull of the moon, assisted by the sun. As the Earth turns, the oceans bulge slightly on the side facing the moon, and again on the opposite side, creating 2 high tides and 2 low tides every day. The timing varies with coastlines and geography, but the principle remains universal. Gravity pulling water into rhythm with the cosmos. Tides are the planet's metronome, setting a tempo that has guided life for billions of years. Shorebirds feed by it, mangroves grow according to it, and even ancient human settlements built calendars around its predictability. To watch a full tidal cycle is to see the earth breathe, the slow inhale of rising water, the long exhale of retreat. Every grain of sand, every pool of tide water participates in that motion. You can almost sense the connection between the moon's silent orbit and the shifting foam around your feet. The rhythm of tides is so steady that time itself seems to bend around it. At night, the sea reveals yet another layer of magic. In many parts of the world, the water glows when disturbed, the light of living organisms known as bioluminescence. Tiny plankton called dinoflagellates produce flashes of blue-green light when jostled by waves or movement. Each one is smaller than a pinhead, but when billions gather, their light can outline every ripple and swirl. A breaking wave becomes a band of stars. A boat's wake leaves a glowing trail like liquid fire. Even the footprints of someone walking along the shore can shine for a moment before fading back into darkness. Bioluminescence is chemistry turned into wonder. The light comes from a reaction between a molecule called luciferin and an enzyme called luciferase, releasing photons instead of heat. It's used by organisms for defense, communication, or simple camouflage. Some deep-sea creatures use it to lure prey, while others flash in patterns to attract mates. But to the human eye, it feels like pure enchantment, the sea whispering back with light instead of sound. Beneath this beauty lies a balance as precise as any clock. Every current, wave, and tide plays a role in distributing energy and nutrients. The surface layers feed on sunlight, supporting blooms of plankton that form the base of the food chain. As these organisms die, they sink, carrying carbon into the depths where it's stored for centuries. The ocean, in that sense, is both mirror and memory, reflecting sunlight while quietly regulating the planet's temperature and chemistry. The ocean's whisper is never quite silent. Even in the calmest moment, it speaks through motion. The faint hiss of receding foam, the low rumble of distant surf, the hum of water against rock. Stand by the shore on a still night, and you can hear it breathe. The air tastes faintly of salt, the horizon shimmers under the moon, and the water stretches beyond sight or comprehension. Beneath your feet, tides are shifting, currents turning, and creatures glowing unseen in the dark. All the layers of the sea, warm, cold, bright, and black, are connected by these quiet rhythms. The waves you see began as wind half a world away. The deep currents below you may not surface again for 1,000 years, and the same moon that pulls the tides above the shore stirs the water miles beneath. The ocean is a whisper that never ends, a voice shaped by gravity, chemistry, and light, speaking softly to every shore it touches. The sky may look empty, but it's filled with motion, an invisible cycle of water rising, cooling, and falling again. Every cloud, every wisp of mist, every droplet on a window begins with a simple act of escape. When sunlight warms oceans, rivers, or even a damp field, water molecules near the surface gain enough energy to break free and drift upward as vapor. They are weightless for a moment, part of the unseen breath of the planet. Yet as they rise, the air cools and expands, and their freedom fades. What was once invisible begins to gather again, tiny droplets forming in the air, each one clinging to something even smaller. For a cloud to exist, vapor alone isn't enough. Water needs a surface to condense on, something to hold on to. The atmosphere provides countless such surfaces in the form of microscopic particles known as condensation nuclei. Dust, pollen, sea salt, smoke, even fragments of volcanic ash. Water vapor condenses around these motes, creating droplets so small that 1,000 of them could fit across the width of a single hair. Millions of these droplets cluster together, scattering sunlight and giving clouds their familiar softness. Once formed, these droplets continue to grow. Some collide and merge, a process called coalescence, while others freeze into tiny ice crystals if the air is cold enough. As they fall and rise within the turbulent air currents of a cloud, they exchange moisture, gain mass, and eventually become heavy enough to overcome the pull of the updrafts holding them aloft. That's when rain begins, not as a single event, but as the collective decision of countless droplets that have finally grown too heavy to stay airborne. Clouds come in families, each one shaped by altitude, temperature, and the moods of the atmosphere. The lowest are the stratus clouds, flat grey blankets that stretch across the sky, muting sunlight into a soft, even glow. They bring calm weather or light drizzle, their movement slow and measured. Higher up, cumulus clouds rise in billows and towers, sculpted by convection. They form when warm air from the ground rises and cools, building those bright, cotton-like shapes that drift through fair weather, or, when energized, grow into towering cumulonimbus clouds that unleash thunder and lightning. Higher still, where the air is thin and cold, wispy cirrus clouds streak the sky like brushstrokes of white paint. Made almost entirely of ice crystals, they glow faintly in the sunlight and often herald a change in weather. Together, these cloud types form a layered tapestry, each telling a story about the state of the air. Meteorologists can read those stories like a script, knowing, for example, that a lowering ceiling of stratus means approaching rain, or that cirrus trails spreading out from the west often signal a coming storm. The atmosphere doesn't reserve its artistry for clouds alone. Sometimes the same process of condensation happens close to the ground, and the result is fog, a cloud that decided not to rise. Fog forms in several ways depending on how the air cools. On calm, clear nights, the ground radiates heat into space, cooling the air just above it until water vapor condenses into droplets. This is radiation fog, the kind that settles in valleys and fields before dawn, wrapping the world in silence. Along coastlines, warm, moist air moving over a cooler surface creates advection fog, the rolling kind that drifts inland like soft smoke, and when air climbs a slope, cooling as it rises, it can form upslope fog, clinging to hillsides in long ribbons that stretch across the landscape. Even when fog doesn't form, the same cooling can create dew or frost, miniature weather events you can touch. On cool mornings you can see dew collecting along grass blades, window panes, or spider webs, tiny beads born from the same process that makes clouds. When the temperature dips below freezing, those droplets crystallize into frost, painting the world in fragile lace. Dew and frost are, in essence, doorstep meteorology, a reminder that the same physics guiding thunderheads and storms also happens quietly in your garden. Not all rainfalls are equal, and understanding their origins reveals just how many stories a single molecule of water can tell. A gentle drizzle forms from small uniform droplets falling through stable air. The drops are light, barely disturbing the surface they land on, more like a soft brushing than a fall. Drizzle tends to come from low stratus clouds, where updrafts are weak and the droplets never grow large. A sudden shower, on the other hand, is born in tall cumulus towers, where powerful convection hurls droplets upward to collide and merge before they tumble earthward. These raindrops are much larger, their paths turbulent, their impact audible. Yet whether in drizzle or downpour, the molecule itself hasn't changed, only the journey it took through air currents and temperature gradients. There's also rain that never touches the ground. In dry regions, droplets sometimes evaporate as they fall, vanishing back into vapor before reaching the surface. This phenomenon, called virga, appears as streaks descending from clouds that dissolve into nothing. It's a kind of atmospheric rehearsal, rain that begins, changes its mind, and returns to invisibility. Every cloud, every mist is temporary, They appear, transform and fade, carried by winds into new formations. Yet their patterns influence everything below them: how sunlight reaches the earth, how temperatures rise and fall, and how ecosystems survive. Even the timing of migrations, flowering and harvests is tied to the moods of clouds. The water cycle isn't just a loop of evaporation and condensation. It's a living rhythm that pulses through air, land, and life itself. At night, this rhythm becomes visible in subtler ways. In mist or light rain, the glow around a streetlight takes on a halo. Each tiny droplet refracts and scatters the light, forming a perfect ring of silver or amber that seems to float in the air. The geometry is simple, but the effect is haunting. Every droplet acts like a lens, bending light at just the right angle to create a circle of quiet brilliance. It's the same optical principle that paints halos around the moon or glories around aircraft shadows in clouds. Simple refraction, multiplied billions of times. Standing in mist, watching that glow, it's easy to forget you're surrounded by chemistry and physics. Yet the beauty of it comes precisely from how ordinary it is. The same condensation that turns vapor into clouds, the same scattering that softens the horizon at sunset. The air itself is alive with water, changing state, forming droplets, and carrying light. Every bead of dew, every patch of fog, every streak of rain is part of a grand balancing act, the Earth's breath made visible. As the mist thickens and the sounds of the world fade, you can almost sense the pulse of the sky above you. Patient, cyclical, and eternal. The droplets hang, merge, and drift, obeying nothing more than temperature, pressure, and chance. A single molecule might rise from an ocean, rest in a cloud, fall as rain, freeze on a leaf, and rise again as vapor. It's the same molecule, endlessly reused, endlessly renewed. And in that gentle glow beneath a streetlight, the entire story of the sky's breath unfolds, quiet, constant, and astonishingly alive. The sky may look empty, but it's filled with motion, an invisible cycle of water rising, cooling, and falling again. Every cloud, every wisp of mist, every droplet on a window begins with a simple act of escape. When sunlight warms oceans, rivers, or even a damp field, water molecules near the surface gain enough energy to break free and drift upward as vapor. They are weightless for a moment, part of the unseen breath of the planet. Yet as they rise, the air cools and expands and their freedom fades. What was once invisible begins to gather again, tiny droplets forming in the air, each one clinging to something even smaller. For a cloud to exist, vapor alone isn't enough. Water needs a surface to condense on, something to hold on to. The atmosphere provides countless such surfaces in the form of microscopic particles known as condensation nuclei. Dust, pollen, sea salt, smoke, even fragments of volcanic ash. Water vapor condenses around these motes, creating droplets so small that 1,000 of them could fit across the width of a single hair. Millions of these droplets cluster together, scattering sunlight and giving clouds their familiar softness. Once formed, these droplets continue to grow. Some collide and merge, a process called coalescence, while others freeze into tiny ice crystals if the air is cold enough. As they fall and rise within the turbulent air currents of a cloud, they exchange moisture, gain mass, and eventually become heavy enough to overcome the pull of the updrafts holding them aloft. That's when rain begins, not as a single event, but as the collective decision of countless droplets that have finally grown too heavy to stay airborne. Clouds come in families, each one shaped by altitude, temperature, and the moods of the atmosphere. The lowest are the stratus clouds, flat grey blankets that stretch across the sky, muting sunlight into a soft, even glow. They bring calm weather or light drizzle, their movements slow and measured. Higher up, cumulus clouds rise in billows and towers, sculpted by convection. They form when warm air from the ground rises and cools, building those bright cotton-like shapes that drift through fair weather, or, when energized, grow into towering cumulonimbus clouds that unleash thunder and lightning. Higher still, where the air is thin and cold, wispy cirrus clouds streak the sky like brushstrokes of white paint. Made almost entirely of ice crystals, they glow faintly in the sunlight and often herald a change in weather. Together, these cloud types form a layered tapestry, each telling a story about the state of the air. Meteorologists can read those stories like a script, knowing, for example, that a lowering ceiling of stratus means approaching rain, or that cirrus trails spreading out from the west often signal a coming storm. The atmosphere doesn't reserve its artistry for clouds alone. Sometimes the same process of condensation happens closer to the ground, and the result is fog, a cloud that decided not to rise. Fog forms in several ways depending on how the air cools. On calm, clear nights, the ground radiates heat into space, cooling the air just above it until water vapor condenses into droplets. This is radiation fog, the kind that settles in valleys and fields before dawn, wrapping the world in silence. Along coastlines, warm, moist air moving over a cooler surface creates advection fog, the rolling kind that drifts inland like soft smoke. And when air climbs a slope, cooling as it rises, it can form upslope fog, clinging to hillsides in long ribbons that stretch across the landscape. Even when fog doesn't form, the same cooling can create dew or frost, miniature weather events you can touch. On cool mornings, you can see dew collecting along grass blades, window panes, or spider webs, tiny beads born from the same process that makes clouds. When the temperature dips below freezing, those droplets crystallize into frost, painting the world in fragile lace. Dew and frost are, in essence, doorstep meteorology, a reminder that the same physics guiding thunderheads and storms also happens quietly in your garden. Not all rainfalls are equal, and understanding their origins reveals just how many stories a single molecule of water can tell. A gentle drizzle forms from small uniform droplets falling through stable air. The drops are light, barely disturbing the surface they land on, more like a soft brushing than a fall. Drizzle tends to come from low stratus clouds, where updrafts are weak and the droplets never grow large. A sudden shower, on the other hand, is born in tall cumulus towers, where powerful convection hurls droplets upward to collide and merge before they tumble earthward. These raindrops are much larger, their paths turbulent, their impact audible. Yet whether in drizzle or downpour, the molecule itself hasn't changed, only the journey it took through air currents and temperature gradients. There is also rain that never touches the ground. In dry regions, droplets sometimes evaporate as they fall, vanishing back into vapor before reaching the surface. This phenomenon, called virga, appears as streaks descending from clouds that dissolve into nothing. It's a kind of atmospheric rehearsal. Rain that begins, changes its mind, and returns to invisibility. Every cloud, every mist is temporary. They appear, transform, and fade, carried by winds into new formations. Yet their patterns influence everything below them, how sunlight reaches the earth, how temperatures rise and fall, and how ecosystems survive. Even the timing of migrations, flowering, and harvests is tied to the moods of clouds. The water cycle isn't just a loop of evaporation and condensation. It's a living rhythm that pulses through air, land, and life itself. At night, this rhythm becomes visible in subtler ways. In mist or light rain, the glow around a streetlight takes on a halo. Each tiny droplet refracts and scatters the light, forming a perfect ring of silver or amber that seems to float in the air. The geometry is simple, but the effect is haunting. Every droplet acts like a lens, bending light at just the right angle to create a circle of quiet brilliance. It's the same optical principle that paints halos around the moon or glories around aircraft shadows in clouds. Simple refraction, multiplied billions of times. Standing in mist watching that glow, it's easy to forget you're surrounded by chemistry and physics. Yet the beauty of it comes precisely from how ordinary it is. The same condensation that turns vapor into clouds, the same scattering that softens the horizon at sunset. The air itself is alive with water, changing state, forming droplets and carrying light. Every bead of dew, every patch of fog, every streak of rain is part of a grand balancing act. The Earth's breath made visible. As the mist thickens and the sounds of the world fade, you can almost sense the pulse of the sky above you, patient, cyclical, and eternal. The droplets hang, merge, and drift, obeying nothing more than temperature, pressure, and chance. A single molecule might rise from an ocean, rest in a cloud, fall as rain, freeze on a leaf, and rise again as vapor. It's the same molecule, endlessly reused, endlessly renewed. And in that gentle glow beneath a streetlight, the entire story of the sky's breath unfolds. Quiet, constant, and astonishingly alive. The sky's never really empty. It's full of drifting water in constant negotiation with sunlight and air. Every cloud begins the same way, with a molecule escaping. When the sun warms a wet surface, some of those molecules slip free and rise as invisible vapor. As the air thins and cools, that freedom falters, they need somewhere to land, and the atmosphere offers countless tiny anchors: dust, pollen, sea salt, smoke. These serve as condensation nuclei, specks on which vapor can settle and turn back into liquid. Each droplet is smaller than a grain of dust, yet billions together become a visible cloud. Inside the cloud, droplets jostle and merge. Collisions build them larger until gravity starts to matter. Some freeze into crystals, others stay liquid, and all drift through swirling currents that lift and drop them in a slow, looping dance. When enough droplets join forces, they fall as rain, the sky's quiet verdict that a cloud has grown too heavy to keep. Clouds come in families, each shaped by altitude and temperament. Stratus clouds spread like grey quilts, softening sunlight into a steady glow. Cumulus clouds billow in heaps, sculpted by rising warm air. When they climb tall enough, they grow into thunderheads that flash and roar. High above, cirrus clouds streak thin and feathery, pure ice crystals brushing the blue like faint handwriting. Every formation speaks of temperature, wind, and humidity, an atmospheric diary written in vapor. Sometimes those clouds refuse to rise at all and settle around us as fog, a cloud at ground level. On calm nights, cooling air breeds radiation fog that pools in valleys before dawn. Over coasts, warm moist air gliding across colder water births advection fog, rolling ashore like breath. Air climbing a hillside forms upslope fog, draping mountains in pale ribbons. When the air cools just enough to condense on leaves or glass, we wake to dew. When it cools past freezing, those droplets crystallize into frost. They're miniature clouds we can touch, proof that the sky's behavior continues at our feet. Rain itself tells multiple stories. Drizzle drifts from low stratus, its tiny drops falling almost weightlessly through still air. Sudden showers descend from towering cumulus, where violent updrafts have forged large, heavy drops that strike the ground with force. Sometimes in dry air, raindrops evaporate before they land. Streaks of ghost rain called virga that fade mid-fall. Different journeys, same molecule. Through these shifting forms, the water cycle keeps time for the planet. Evaporation, condensation, and precipitation pulse like a heartbeat that never stops. Clouds moderate sunlight, ferry heat, and feed rivers. Fogs moisten forests and coasts. Rains refresh soils and seas. Each act in the cycle folds quietly into the next, a choreography as old as air itself. On misty nights the physic becomes art. A halo forms around a street lamp when countless droplets scatter its light in a perfect circle. The same geometry paints halos around the moon, and glories around airplane shadows. Each droplet bends and reflects light at just the right angle. Millions together create the illusion of a luminous ring, its simple optics made magical by scale. Stand beneath such a glow and you can feel the atmosphere breathing around you, vapor condensing, droplets drifting, light sifting through a sky that's never still. The same water rising now from a puddle may someday snow onto a mountain or bead on a window thousands of kilometers away. Every wisp of mist, every pearl of dew, every streak of rain is one line in the sky's long exhale. And beneath the halo's quiet shimmer, you witness that breath made visible, soft, endless, and beautifully alive. Inside every living cell, water is far more than a backdrop. It is the stage, the actor, and the invisible hand that keeps the whole performance running. Every heartbeat, thought, and movement begins in an ocean too small to see. A warm, liquid world where chemistry becomes life. Cells are often described as bags of molecules, but that image misses the truth. They are more like tiny tide pools, filled with organized water in constant shimmering motion. Biochemists sometimes call water the universal solvent, but in living systems it is also an active participant. It dissolves nutrients, carries ions, cushions proteins, and mediates reactions. In many ways, life itself can be defined as the chemistry of water behaving in extraordinarily complex ways. Take the simple fact that cells stay fluid at room temperature, while other mixtures might congeal or crystallize. That's because water's polarity allows it to stabilize thousands of compounds simultaneously. Sugars, salts, amino acids, and nucleotides all rely on water's gentle grip to stay mobile and reactive. But water's most astonishing contribution to biology is not in what it holds, it's in what it organizes. Consider the hydrophobic effect, one of the quiet forces behind every living membrane. Some molecules, like fats, dislike contact with water. Their long uncharged tails have nothing for water molecules to grab onto. When dropped into a watery environment, they huddle together, turning their hydrophobic sides inward and their hydrophilic heads outward. This spontaneous self-assembly forms the membranes that enclose cells, not through brute force, but through water's subtle preference for its own company. It's the liquid deciding in effect to exclude what doesn't fit. The same principle shapes the proteins that perform nearly all of life's work. Proteins are long chains of amino acids that fold into intricate three-dimensional shapes. Water guides that folding by nudging hydrophobic parts inward and hydrophilic parts outward. Each protein's final structure is like a sculpture carved by water's preferences, a delicate balance of attraction and avoidance. If the surrounding water changes, say, through heat, acidity, or salt, the folding falters and the protein unravels. In that sense, every heartbeat depends on the quiet discipline of liquid structure. Even enzymes, the catalysts that speed up life's reactions, depend on water, not just as a solvent, but as a collaborator. Around every enzyme sits a thin shell of organized water molecules known as the hydration layer. These molecules are not random. They form a flexible, shifting scaffold that helps stabilize the enzyme's shape and guide its chemistry. When a reaction occurs, when one molecule must bind, change, and release, the hydration layer rearranges itself, cushioning every movement like a fluid cushion of precision. Water, in these moments, is both stage and dancer. One of the most fascinating ways water participates in life's chemistry is through the movement of protons, single hydrogen ions that hop from molecule to molecule in a process known as the Grotthus mechanism. In simple terms, a proton doesn't swim through water like a tiny particle. It leaps from one water molecule to the next, passing along a chain of bonds almost instantaneously. It's less like a ball rolling across a field and more like a spark jumping down a wire. This rapid proton transfer underlies how acids behave, how enzymes work, and even how energy moves through biological membranes. Energy in cells is often stored and released through reactions involving water. The best known of these is the hydrolysis of adenosine triphosphate, or ATP, the universal energy currency of life. ATP holds energy in its high-energy phosphate bonds, and when one of those bonds is broken by the addition of water, the molecule releases a small but precise burst of energy. It's not an explosion, but a click, a molecular trigger that powers muscle contractions, nerve impulses, and countless cellular reactions. Water doesn't merely witness this exchange, it performs the action itself. Each hydrolysis is like a drop of water turning a gear, powering life in silence. Inside the cell, water also provides the medium for diffusion, the quiet drifting of molecules from crowded spaces to emptier ones. It's how oxygen reaches enzymes, how nutrients spread through cytoplasm, and how waste finds its way out. The cell's watery interior, known as cytosol, might look chaotic, but its motion is remarkably organized. Large molecules move slowly, small ions dart quickly, and the whole mixture vibrates with microscopic currents. Under an electron microscope, even the most tranquil cell is a world in flux. Water's presence also softens biology's edges. It dampens heat, moderates pH, and prevents sudden chemical shocks. Reactions that would tear molecules apart in dry conditions proceed gently in water, their energies absorbed and released with balance. Hydrogen bonds form and break countless times per second, holding molecules close but never rigidly. This flexibility allows cells to be both stable and responsive, ready to change but not to collapse. Some scientists describe living water as structured, though not in the rigid sense of ice. Around membranes and proteins, water molecules line up briefly, forming layers that behave differently from bulk liquid. These microscopic patterns help channel ions, guide reactions, and stabilize large complexes. They last only trillionths of a second, yet together they give life its coherence, an unbroken web of connection from molecule to molecule. Think of a single cell as a tide pool enclosed by a membrane, warmed by energy and stirred by internal currents. Within it, every process, from respiration to replication, happens in water. DNA twists and unwinds in water. Ribosomes knit proteins in water. Mitochondria spin gradients of protons across water-filled membranes. Life is not built in water as much as out of it. Even death, in a biochemical sense, is the moment when water's choreography stops. When ions no longer move, proteins cease folding, and hydrogen bonds fall still. Until that point, every flicker of existence depends on this simple liquid maintaining its improbable balance of order and freedom. It's easy to forget that the same substance in oceans and raindrops also fills the space inside you. Every heartbeat stirs more than 5 liters of water through your veins. Every thought depends on water molecules passing signals between neurons. You are, at every scale, a mobile ocean contained by skin. If you could shrink small enough to stand inside a living cell, it would feel like stepping into a warm, quiet tide pool. Softly lit, endlessly moving, and filled with the chemistry of life in slow suspension. Molecules would drift by like drifting plankton, enzymes would flex and twist, and the water itself would shimmer with energy transfers too small to see. Within that gentle tide, existence unfolds molecule by molecule, powered by the same substance that carves rivers, lifts clouds, and falls as rain. Water, the humble molecule, is life's oldest collaborator, the ocean from which every heartbeat still begins. Long before continents had names or skies turned blue, there were only shallow pools and restless tides. In those ancient waters, sunlight, minerals and chemistry mingled endlessly. Simple molecules colliding, joining, breaking apart, and trying again. Over countless cycles of evaporation and rain, these pools concentrated life's ingredients. Fatty acids assembled into tiny bubbles, amino acids linked into chains. Within these fragile boundaries, reactions began to sustain themselves, and the first protocells took shape. It was in water that lifeless chemistry first became capable of memory, capable of evolving. The earliest living systems were almost certainly aquatic, born in places where water moved gently enough to nurture, but wildly enough to stir. Some theories place this origin near volcanic vents on the seafloor, where minerals provided structure and energy. Others favour tide pools along rocky shores, where sunlight, salt, and cycles of drying and refilling offered both stability and challenge. Whichever cradle it was, the common thread was liquid water, the solvent that made movement, interaction, and complexity possible. Without it, life's fragile molecules would have remained scattered dust, unable to organize into something greater. Once the first living cells appeared, water continued to shape every step of their story. Oceans became the stage for the earliest ecosystems, floating gardens of bacteria and algae, harvesting sunlight, feeding on minerals, and releasing oxygen into the air. That transformation slowly filled the atmosphere with breathable gas, paving the way for new possibilities. For more than 2 billion years, everything alive lived entirely surrounded by water. It provided protection, buoyancy, and stability, a constant environment where gravity's pull was gentle and temperature swings were softened. But evolution thrives on challenges, and eventually some creatures began to test the boundaries of their aquatic home. In coastal shallows and river deltas, fish-like animals developed stronger fins to push through dense vegetation and shallow mud. Their lungs, originally adaptations for gulping air in oxygen-poor waters, became tools for breathing above the surface. Step by slow step, waterborne anatomy adapted for life on land. Yet even as these pioneers crawled ashore, they carried their origins with them. The fluids in their veins kept the same balance of salts and minerals as seawater. Every cell inside them remained an ocean in miniature. To this day, your own bloodstream mirrors that ancient chemistry, sodium, chloride, potassium, and calcium, dissolved in precise proportions, echoing the first seas. Water continued to dictate how life could reproduce and spread. Early organisms relied entirely on liquid to transport their genetic material. Eggs and sperm were released into the sea, drifting until chance brought them together. As life ventured onto land, that dependence became a challenge to solve. Amphibians still needed water to lay their eggs, but reptiles evolved a way to bring water with them. The amniotic egg, a tiny self-contained pond sealed in a shell, allowed embryos to develop safely on dry ground. Plants faced a similar dilemma. Ferns and mosses still rely on water for reproduction, their sperm swimming through droplets to find an egg. Later plants, like conifers and flowering species, evolved pollen and seeds, ways to protect and deliver life's essence without needing a puddle or a raindrop. Each innovation was a negotiation with water. How to live without it, yet never truly leave it behind. Even the sensory worlds of animals have been shaped by their relationship with water. For fish, sound and pressure move through water much faster and farther than in air. They sense these vibrations through a special organ called the lateral line, a series of tiny pores along their bodies that detect subtle movements in the surrounding water. It's an ancient form of perception, a way of feeling the world rather than seeing it. When some species left the water, they had to reinvent hearing for air. The bones that once supported gills were repurposed to transmit vibrations in a new, thinner medium, eventually becoming the inner ear structures of amphibians, reptiles, birds and mammals. In that sense, every whisper, song or heartbeat you hear today is a distant descendant of the water's murmur. Other senses changed too. Eyes that first evolved to detect light underwater had to adapt to the brighter, refracted world above the surface. Smells that once travelled as dissolved molecules in liquid had to be detected as gases. Even the act of breathing became a controlled version of evaporation, lungs drawing in air and protecting delicate, wet tissues from drying out. Life's transition to land was not a single leap, but a series of accommodations, each one preserving a little piece of the ocean inside. Throughout evolutionary history, water has acted not just as a setting, but as a creative pressure, rewarding flexibility, cooperation, and resilience. In aquatic environments, organisms learn to use buoyancy to grow large, to use flow to disperse offspring, and to rely on diffusion for nourishment. On land, they learn to conserve, retain, and recycle that same precious fluid. Whether it's a cactus storing moisture in its flesh, or a camel's blood adjusting its viscosity to heat, every adaptation on Earth reflects some dialogue with water. Even extinction events have followed its patterns. Rising and falling sea levels opened and closed migration routes. Shifting currents change climates, isolating species and forcing them to evolve or vanish. The chemistry of the ocean itself, the balance of carbon, oxygen and minerals, has guided the tempo of evolution, setting the stage for bursts of diversity and long ages of stillness. Water's constancy gives life stability, but its movements also create opportunity. It is both cradle and crucible, patient enough to nurture, restless enough to test. On the cellular level, the story never stopped. Inside every creature alive today, water still drives the fundamental chemistry of existence. It fuels metabolism, regulates temperature, and facilitates the reactions that sustain life. The oldest evolutionary lesson of all, that stability depends on fluidity, remains true from the smallest bacterium to the largest whale. Imagine now the shoreline where this transformation began. Waves lapping against mud, the air thick with humidity and promise. In the shallows, a creature half fish, half experiment braces itself against gravity and pushes upward, its fins splay wide, pressing into wet sand. Behind it, the water ripples, still calling. Ahead lies an unfamiliar world of air and sunlight. Each step forward marks not a break from the sea, but a continuation of its story. The same water that once surrounded it now flows inside it, carried in blood, in cells, in every breath. That moment, fins pressing into mud, footprints glistening at the tide's edge, captures the heart of evolution. Life didn't conquer water, it learned to bring it along. From pools to oceans, from currents to veins, from waves to footsteps, the chemistry of that first drop still moves through everything alive. Every drop of seawater is more complex than it looks. What seems like clear, blue emptiness is in fact a living solution, a soup rich with minerals, gases and drifting life. It's both chemistry and community, a fluid archive of everything the ocean has touched. Within it are the nutrients that feed plankton, the salts that shape circulation, and the carbon compounds that quietly regulate the planet's climate. The ocean's chemistry begins with its salt, but it doesn't end there. Sodium and chloride make up most of the mix, yet dissolved within every litre are dozens of trace elements: calcium, magnesium, potassium, sulfate, and bicarbonate among them. Some occur in concentrations so small they're measured in parts per billion, but each plays a role in maintaining balance. These ions act as both building blocks and buffers, allowing life to grow and reactions to proceed at just the right pace. The sea's composition is surprisingly stable, kept in equilibrium by a continuous exchange between rivers, atmosphere, and the rocks beneath the waves. At the heart of this chemical balance lies the carbonate system, the quiet chemistry that governs how the ocean breathes carbon dioxide. When carbon dioxide from the air dissolves in seawater, it forms carbonic acid, which quickly splits into bicarbonate and carbonate ions. This simple reaction acts as a buffer, resisting sudden swings in acidity and helping the ocean store vast amounts of carbon. Coral reefs, shells, and even microscopic plankton depend on this process to build their calcium carbonate skeletons. Without it, the sea would swing between extremes, too acidic one day, too basic the next. Instead, the ocean remains patient and steady, holding the world's carbon in gentle suspension. Floating within this solution are the ocean's smallest engineers, the plankton. They drift with currents, too small to fight them, yet they shape the chemistry of the entire planet. Phytoplankton, the microscopic plants of the sea, use sunlight to pull carbon dioxide from the water, releasing oxygen and forming the base of almost every marine food chain. Their counterparts, zooplankton, graze on them in endless miniature feasts, transforming the energy of light into forms that larger creatures can use. A teaspoon of seawater may contain millions of plankton, each one working quietly, endlessly, and without recognition. When plankton die or produce waste, their remains begin a slow descent through the water column. This steady fall of organic matter is known as marine snow, a delicate blizzard of carbon-rich particles drifting toward the abyss. Under moonlight, if you could follow it, the effect would be ghostly, flakes of white and silver tumbling through the dark, feeding the depths below. What begins as sunlight at the surface ends as nourishment in the deep ocean, connecting every layer of life in a continuous rain of carbon. Marine snow fuels one of Earth's most intricate food webs. Tiny crustaceans rise from the depths each night to feed on the drifting particles, only to sink again before dawn. Fish and jellyfish follow, and larger predators track their movements in turn. It's an invisible migration, happening every 24 hours, the largest mass movement of life on the planet. From the surface to the midwater twilight, every species participates in a chain of exchange, transforming sunlight into motion, waste into energy, and decay into renewal. Coral reefs and shell-building organisms add structure to this living soup. Corals are colonies of tiny polyps that secrete calcium carbonate skeletons, gradually forming vast underwater cities. Over centuries, their slow construction gives rise to reefs that host thousands of species: fish, crustaceans, sponges, and mollusks, all living within the calcium architecture shaped by chemistry and time. Shellfish, too, borrow ions from seawater to build their protective homes. When they die, their shells settle and dissolve, returning those minerals to the sea. Every reef and beach is part of the same quiet cycle of borrowing and giving back. Deeper down, where sunlight fades to blue and then to black, the ocean changes mood. This is the twilight zone, a region of muted light between about 200 and 1,000 meters deep. Here, photosynthesis stops, but life persists. Creatures glow with bioluminescence, flickering signals in a dim expanse. The water is cool and still, layered in gradients of temperature and density. Marine snow drifts through like falling dust, and the animals here, lanternfish, siphonophores, comb jellies, wait patiently for whatever nourishment descends from above. The deeper one goes, the quieter the ocean becomes. Sound replaces sight, and survival slows to a rhythm measured in heartbeats per hour. Far below the twilight zone lies the true abyss, a world of near-total darkness. Here, the rain of marine snow becomes a fine mist, settling gently over the seafloor. The sediments build over eons, dust from the surface, shells from plankton, fragments of volcanic ash, even traces of meteorites. The ocean floor is an archive written in layers, each centimetre recording years of chemistry and climate. In this silent environment, microbes still thrive, breaking down the final remnants of organic matter. They work so slowly that a single layer of sediment may represent centuries of quiet activity. Even here, the sea does not rest. It recycles, remembers, and continues its invisible labour. Water connects it all, from the shimmer of the surface to the cold calm of the abyss. Every molecule of carbon fixed by plankton eventually returns as carbon dioxide. Every shell that falls becomes part of the ocean's memory, storing information about past climates and future trends. The sea's chemistry, endlessly dynamic yet remarkably balanced, ensures that the planet's systems remain in sync. Imagine drifting downward through this layered world. At the top, sunlight flashes from ripples, turning each wave into a sheet of liquid glass. Schools of fish flicker beneath you, and tiny plankton spin in invisible whirlpools. Descend a little deeper and the light softens to green, then blue, until colours fade and outlines blur. You pass through the thermocline, where warm surface water gives way to cool depths. The pressure grows and the sounds change. Distant clicks, faint groans of unseen creatures, the hum of the ocean itself. Soon you enter the twilight, where life glows with its own light, and the surface above becomes only a memory. Marine snow drifts past like ash in slow motion. Each flake is a story, a particle of once living matter on its way to become something new. Below that, the darkness becomes complete, and only the occasional spark of bioluminescence breaks the black. It's a world without sunlight, but not without purpose. A living night sustained by chemistry and patience. At last you reach the seafloor, where the snow settles into stillness. The pressure is immense, the cold absolute, yet life persists even here. Microbes, worms, and fragile corals thriving on the faint rain from above. The ocean's surface may glitter and change with every gust of wind, but its depths are timeless. Between those extreme, from sparkle to silence, lies the full story of seawater, a living soup where chemistry, life, and time blend seamlessly, feeding both the planet and the imagination. The human body is often described as being mostly water, and that's no exaggeration. By mass, nearly 2/3 of you is liquid, not just sloshing around in obvious places like blood or saliva, but locked within cells, cushioning organs, and quietly moving between every tissue. It's the same molecule that fills oceans and falls as rain, now organised into one of nature's most intricate hydraulic systems. Water is your body's transport network, thermostat, and shock absorber all at once, and every heartbeat, breath, and blink depends on it flowing smoothly. Inside this watery world, your body organises fluid into different compartments. Most of it, about 2/3, lives inside your cells, the intracellular fluid. This is where the chemistry of life happens, enzymes working, ions moving, energy being made. The remaining third lies outside the cells, divided between the spaces in your tissues and the plasma that circulates in your blood vessels. Though separated by membranes, these compartments are in constant conversation. Water moves between them through osmosis, the simple but elegant rule that water always travels toward higher concentrations of dissolved substances. It's nature's way of evening the score. Imagine a cell as a small water balloon surrounded by a salty solution. If the outside becomes saltier, water leaves the cell to balance things out, and the balloon shrinks. If the outside is too dilute, water rushes in, and the cell swells. Osmosis ensures that no compartment gains or loses too much fluid, maintaining a delicate equilibrium that allows everything from nerve impulses to muscle contractions to function correctly. It's quiet, invisible work, but without it, you'd either shrivel or burst. The main players guiding this balance are electrolytes, ions like sodium, potassium, calcium, and chloride. They act as the body's chemical currency for water movement and electrical activity. Sodium, mostly outside cells, draws water toward it and helps regulate blood volume and pressure. Potassium, mostly inside cells, keeps nerves firing and muscles contracting smoothly. Calcium controls heartbeat and bone strength. Chloride helps maintain acidity levels. Together they turn plain water into a carefully tuned physiological solution. Lose too much salt through sweat or illness, and water distribution falters, replenish it, and the system hums back into rhythm. Thirst, meanwhile, is your body's gentle alarm, not a siren but a polite nudge. Specialized sensors in the brain's hypothalamus monitor the concentration of solutes in your blood. When that concentration rises, meaning you've lost water or consumed too much salt, these sensors trigger the sensation of thirst. It's your cue to sip, not gulp. By the time you feel parched, your body has already borrowed fluid from various compartments to keep vital organs stable. A single glass of water can begin to restore balance within minutes, easing that subtle tension as your cells rehydrate. Water also plays a starring role in regulating temperature, a task so routine that it's easy to forget how miraculous it is. The human body operates best around 37 degrees Celsius, and water's high specific heat capacity makes that stability possible. When internal temperature rises from exercise, heat, or stress, water carries excess heat to the surface through the bloodstream. The skin's blood vessels widen, and sweat glands excrete water mixed with salts. As sweat evaporates, it carries heat away, cooling the skin and, in turn, the blood beneath it. It's an elegant feedback loop. Your body sheds liquid to protect itself, then reminds you, via thirst, to replace what's lost. Recovery after exertion depends on the same principle. After exercise, your blood is thicker, your electrolytes diluted, and your internal balance slightly off. A few gulps of water, ideally with a pinch of salt or trace minerals, begin to restore that equilibrium. The water you drink becomes plasma within an hour, circulating through your veins, entering cells, and quietly resetting the chemistry of comfort. It's the body's most natural repair process. No magic powders required. Beyond survival, water finds its way into the rituals of comfort and care. A bowl of soup, for example, is chemistry you can eat. Liquid carrying electrolytes, heat, and nourishment in perfect proportion. Tea does something similar, turning water into a gentle solvent for flavors and aromas that calm the mind. Baths and showers, too, aren't just about cleanliness. They're about returning the body to its natural element. Warm water relaxes muscles and widens blood vessels, improving circulation. Cool water sharpens alertness and seals in calm. Every culture, from Roman baths to Japanese onsen, has discovered that soaking in water feels like pressing the reset button on the nervous system. Even breathing depends on water. The air you inhale must be humidified before it reaches the delicate tissues of your lungs. Without that moisture, each breath would feel dry and harsh. Inside your respiratory system, A thin film of water captures dust and microbes, keeping airways clear. The simple act of exhaling releases tiny droplets of this internal moisture, a visible reminder on cold days that we're constantly exchanging water with the world. Of all the organs that depend on this balance, none are more spoiled than the brain. Roughly 3/4 of it is water, and it's kept at an almost absurdly stable temperature. Neurons send electrical impulses only when their surroundings are just right, not too concentrated, not too dilute. Even a small drop in hydration can cloud thinking and slow reaction times. It's as if the brain insists on premium conditions for performance. Nature's ultimate waterbed, designed for thought instead of sleep. When hydrated properly, it hums quietly, regulating mood, focus, and creativity with liquid precision. The heart, too, owes its rhythm to water. Blood, that crimson river, is mostly plasma, a solution of salts, proteins, and water that delivers oxygen and nutrients. With every beat, it carries heat outward and brings cooled blood back in. The kidneys act as the great regulators, filtering more than 180 litres of fluid a day, reclaiming nearly all of it, and excreting only what's necessary to maintain purity. Their work is meticulous. Too much retention, and pressure builds. Too much loss, and the system dries. It's balance on a cellular scale, practiced millions of times a day without a single conscious thought. Water doesn't just move through you, it is you in motion. It carries your chemistry, supports your organs, and softens every mechanical movement from blinking to breathing. It's the medium through which emotions show themselves. The tear, the flushed cheek, the cool sweat of relief. When you drink, you're not just quenching a need. You're participating in an ancient ritual that every living thing shares. Think of it this way. Inside you, there are tides. Fluid rises and falls, heat shifts, ions drift like currents between shores. The same physics that moves oceans keeps your cells alive. From the first sip of water in the morning to the last exhale at night, the rhythm continues, quiet, steady, and vital. Your body, in its essence, is a walking ocean, self-contained, self-regulating, and always seeking equilibrium. And if you ever forget that, just remember, your brain, nature's premium waterbed, is floating you gently through every moment of it. People often say that water has no taste, that it's neutral, blank, a backdrop for other flavours. But anyone who's travelled knows that's not quite true. A sip from a mountain spring tastes different from a glass drawn from a tap by the sea. Even bottled waters, stripped and filtered, have personalities, some crisp and mineral, others soft and almost sweet. What we call the taste of nothing is really a conversation between minerals, temperature, and memory. Chemically pure water is a rarity outside the laboratory. In nature, it's always flavoured by its journey, the rocks it's touched, the air it's passed through, the pipes it's travelled along. Calcium and magnesium lend hardness, a faint chalky edge. Sodium adds smoothness, while trace metals like iron give a metallic tang. Even temperature changes perception. Cold water feels fresher because low temperatures dull the taste buds that detect bitterness. That's why icy water can make even simple tap water seem luxurious, while warm water reveals every mineral note like a well-aerated wine. Context matters too. The same water that tastes ordinary at home can feel extraordinary when sipped after a hike or during a long drought. Our senses intertwine with emotion. Thirst amplifies gratitude. A single cool mouthful after exertion can feel as rich as a feast. In that moment, the taste of water isn't just chemical, it's psychological. It's the flavour of relief. Beyond taste, water engages us through sound, an entire language of calm built from motion. Rain on rooftops, fountains in courtyards, the hush of waves rolling beneath wooden piers. Each sound is familiar, yet endlessly varied. Part of their magic lies in their unpredictability. Raindrops strike surfaces at random intervals, forming patterns that never quite repeat. The brain, tuned to seek rhythm and meaning, relaxes when it can't predict the next sound. Instead of tension, it feels release. This randomness, wrapped in gentleness, is why water sounds are used to soothe newborns, lull travellers to sleep, or mask the noise of restless cities. Fountains have spoken to people for centuries. In ancient Rome, they were feats of engineering. Water delivered through aqueducts, made to leap from marble mouths and spill into basins. In Islamic gardens, fountains served a different purpose, symbols of paradise, their quiet streams creating a sense of endless renewal. Even today, a trickling fountain in a courtyard can make an enclosed space feel open, alive. It's not just decoration, it's the soft heartbeat of water reminding the mind to slow down. Waves tell a different story. Under piers or along rocky coasts they form deep, rhythmic pulses, a low music shaped by gravity and wind. Each crash, each retreat, follows physics but feels like emotion, a conversation between the ocean and the shore. People instinctively synchronize their breathing to that rhythm. Studies show heart rate and stress levels fall when we listen to waves. The sound of the sea may be the closest thing nature offers to a lullaby written for adults. Across cultures, people have built rituals around water's presence. In Japan's tea ceremony, water is treated not as a background element, but as the central performer. The sound of it pouring from bamboo ladles, the shimmer of steam rising from the kettle, the ripples in a ceramic bowl. Every movement is deliberate, every detail a small act of reverence. The ceremony is less about drinking and more about witnessing transformation. Cold water warmed, powder whisked into suspension, stillness turned to motion. In Europe's thermal baths, water plays another role, that of healer. Since Roman times, people have gathered in hot springs to soak away pain and worry, trusting that minerals and warmth together could restore balance. Modern science confirms some of that intuition. Immersion in warm water dilates blood vessels, slows heart rate, and releases endorphins. But even without the chemistry, there's comfort in the ritual itself. The steam, the hum of voices, the sense of floating weightless in shared silence. In temples, monasteries and gardens around the world, still pools serve as mirrors for contemplation. They offer reflection in more ways than one. The faint shimmer of light on water invites the gaze inward. The smallest ripple reminds us how easily calm can be disturbed and restored. Psychologists suggest that humans may be drawn to these scenes because our brains evolved alongside water. For early humans, the presence of water meant safety. Drinking, food, shelter. Even now, our nervous systems recognize that signal of security. When we see or hear water, ancient instincts whisper, "You're safe here." Modern neuroscience gives that intuition a clearer frame. Viewing or listening to water activates parts of the brain linked with calm focus and reduced activity in the amygdala, the region that processes fear and anxiety. Slow, natural rhythms, like waves or flowing streams, encourage synchronization between heart rate and breathing, a pattern associated with relaxation. In a sense, water trains the brain to idle smoothly, neither racing nor stalling, just flowing, much like the liquid itself. That's why screensavers of rippling ponds, recordings of rainstorms, and even small tabletop fountains can feel so strangely soothing. They echo the real sensory cues that once told our ancestors, "Rest. The world is kind for a moment." Whether it's the sight of light moving across a pond or the distant rhythm of surf, water gives the brain permission to let go of vigilance. Of course, water's emotional weight isn't only peaceful, it can also stir nostalgia. The smell of rain after a dry spell, that earthy electric scent called petrichor, is one of the most powerful memory triggers known. It carries hints of ozone and plant oils released from soil, scents that our brains link with renewal. The moment those molecules hit the nose, time collapses. We remember summers long gone, first storms, the sound of gutters overflowing. Even without seeing the rain, the scent tells the story. The world is washing itself clean. Water, in all its forms, connects the physical to the emotional. The sound of a kettle beginning to hiss, the feel of steam against the skin, the sight of raindrops racing down glass. These sensations remind us that we are made of the same material they describe. To find comfort in water is to find comfort in continuity, in the cycle that has always sustained us. And so the taste of rain is never just taste. It's memory and motion, temperature and texture, carried in one quiet mouthful. Whether it's the mineral tang of a storm puddle or the smooth neutrality of filtered water, what we sense is context. The world distilled. Picture a quiet evening, a glass of cool water beside you, condensation fogging its sides. You take a sip, set it down, and watch as tiny droplets slide down the glass like threads of light. Outside, perhaps there's a faint drizzle tapping at the window, or the hum of distant traffic softened by moisture in the air. For a moment it's easy to forget everything complicated. Between sips, the world feels simple again, clean, calm, and quietly alive. When astronomers talk about the search for life beyond Earth, they often sum it up in 3 simple words: follow the water. It's not because water guarantees life, but because everywhere life exists on Earth, water is part of the story. It dissolves nutrients, moderates temperature, and gives molecules the freedom to move and interact. So when we look to the stars, we look for that same signature, a hint that somewhere, something might be stirring in liquid form. The first clues don't come from telescopes that take pictures, but from those that take spectra, instruments that break light into its component colours. Every element and molecule absorbs light in a unique way, leaving behind dark lines known as spectral fingerprints. Water vapour has a particularly recognisable set of these marks, appearing in both infrared and visible light. When starlight passes through a planet's atmosphere, some wavelengths are absorbed by water molecules, creating a pattern that tells us, across unimaginable distances, that water is there. One of the simplest ways astronomers detect this is through what's called a transit spectrum. When a planet passes in front of its star, a tiny fraction of the starlight filters through the planet's atmosphere before reaching us. By comparing the light before, during, and after the transit, scientists can detect which wavelengths have been absorbed, effectively reading the ingredients of that distant atmosphere. It's like holding a glass of water up to a light and identifying its contents from the colour it casts on the wall. Through this method, telescopes like Hubble and more recently the James Webb Space Telescope have spotted water vapour in the skies of faraway worlds. Some of these planets are gas giants too hot for life, where water exists as fleeting steam. Others are smaller, with clouds and haze that hint at conditions more Earth-like. Even if the water is high above boiling or locked in ice, the discovery tells us something important. The chemistry for habitability exists beyond home. Direct imaging, actually seeing exoplanets as tiny specks of reflected starlight, adds another layer to this detective work. By analysing the faint glow from these worlds, astronomers can infer surface properties, cloud compositions, and even temperature gradients. In some cases, subtle reflections reveal patches of ice or glints of liquid. These glimmers, though rare and faint, are like whispers from distant shores. Each detection reminds us that water is not an earthly anomaly but a cosmic habit. Evidence doesn't just come from afar, it arrives, quite literally in our hands. Many meteorites that fall to Earth contain hydrated minerals, rocks that once reacted with liquid water. Some even hold microscopic inclusions of frozen brine, trapped for billions of years inside. These fragments suggest that asteroids and comets once carried, and still carry, water through the solar system. It's thought that much of Earth's own supply may have arrived this way, a long reign of icy messengers delivering the ingredient life would later depend on. Closer to home, several worlds within our solar system are now known to hide vast oceans beneath their surfaces. Europa, one of Jupiter's moons, wears a crust of ice laced with cracks where salty water wells up from below. Saturn's moon, Enceladus, sprays jets of vapour and ice crystals into space through fissures at its south pole, forming a misty halo that has been directly sampled by spacecraft. Even distant Titan, wrapped in an orange haze, has liquid on its surface, though there it's methane and ethane, not water, flowing through carved valleys and lakes. Each discovery expands our understanding of what ocean can mean. Yet the mantra, "follow the water," carries a necessary caution. Water might make life possible, but it doesn't make life inevitable. Venus almost certainly had oceans once, but its runaway greenhouse effect turned them to vapour long ago. Mars too shows signs of ancient rivers and deltas, their beds now fossilised into rust-red stone. Both worlds had the same basic ingredients as Earth, but a slightly different balance of heat, pressure, and magnetic shielding led to very different fates. Water alone sets the stage, it does not write the play. Still, the presence of water gives us reason to wonder, if it can exist in so many places, under ice, in vapour, dissolved in minerals, then perhaps, somewhere, it has found the conditions to flow freely and stay stable long enough for chemistry to bloom into something more. That hope drives missions across the solar system and the design of telescopes aimed far beyond it. Each new detection of a watery signature, whether in the clouds of a distant planet or the fractures of an icy moon, nudges that possibility a little closer to belief. In the laboratory, scientists are now recreating alien oceans, mixing salts, organic compounds, and exotic ices to test how chemistry might unfold under strange skies. They simulate the crushing pressures of Europa's depths, the frigid methane seas of Titan, and even the acid clouds of Venus. What emerges isn't life, but possibility. Hints that water, in its many forms, remains the universe's great experimenter. The search is not just scientific, it's also deeply human. When we look for water beyond Earth, we're looking for reflection, a reminder of home. Oceans, after all, are what connect our planet's continents and civilizations. To imagine another world with its own tides and storms is to imagine another version of ourselves, watching their sky and wondering the same thing. Picture for a moment what it might feel like to stand beneath an alien drizzle. The drops fall more slowly than Earth's, thickened by a heavier atmosphere, each one glinting faintly under a dim red sun. The air smells of minerals, the sky an unfamiliar hue. You reach out a hand and catch a droplet, cool, dense, slightly oily perhaps, but recognisably water. Around you, the landscape is silent except for that soft rhythmic patter. In that sound, across light years, something universal speaks. That imagined moment captures the heart of exploration. We search for extraterrestrial oceans not just to confirm that water exists elsewhere, but to understand our place in a universe that seems inclined toward it. From comets and moons to exoplanets and spectral lines, the cosmos keeps whispering the same story, that the substance which shaped us is far from rare, and somewhere perhaps, under another sky, water may be tracing patterns in the dust waiting for its next great experiment to begin. Far beyond the warmth of the sun, where sunlight is little more than a faint gleam, several moons keep secrets beneath their frozen surfaces. They look lifeless from afar, pale spheres of ice and shadow orbiting the giant planets, yet beneath those crusts may lie vast hidden oceans. The outer solar system, once thought too cold for anything resembling activity, now seems alive with possibility. Among its most intriguing worlds are Europa, Enceladus, Titan, Ganymede, and Callisto. Moons that prove water, or something like it, can thrive even in eternal twilight. Europa, a moon of Jupiter, may be the most famous of these frozen worlds. Its surface is a cracked sheet of ice, streaked with rust-coloured lines that look like fractures in glass. From orbit, it resembles a frozen eye gazing back at the universe. Those lines aren't scars from impacts, they're signs of movement. The ice shell is thought to float atop a global ocean, kept liquid by the gravitational tug-of-war between Jupiter and its neighbouring moons. This constant flexing, known as tidal heating, generates enough warmth to melt the ice deep below. The ocean beneath Europa's crust might be 100 kilometres deep, more than twice the volume of all Earth's oceans combined. And it isn't just plain water. Observations from spacecraft suggest it's briny, rich in salts, and possibly other chemicals leaching from the rocky seafloor below. Through cracks in the ice, geysers may occasionally erupt, spraying vapour and microscopic ice grains into space. When NASA's Galileo spacecraft and later the Hubble Space Telescope studied these plumes, they detected signs of sodium chloride, the same salt that seasons our oceans, and traces of organic molecules. For a world so far from the Sun, Europa feels surprisingly familiar. Enceladus, a tiny moon orbiting Saturn, tells a similar story on a smaller scale. Barely 500 kilometres across, it should have long since frozen solid. Instead, it behaves like a living world. In 2005, the Cassini spacecraft discovered towering plumes of water vapour and ice particles erupting from fissures near its south pole. Features now called the tiger stripes. Cassini flew directly through those plumes, tasting their chemistry. Inside were water vapour, salts, silica particles, and complex organic compounds. The ratio suggested that liquid water, heated by tidal flexing, was in contact with a rocky core. In other words, Enceladus doesn't just have an ocean, it may also have underwater vents similar to those on Earth's seafloor, the kind that teem with microbial life here at home. If any place beyond Earth could host living chemistry, Enceladus is near the top of the list. Beneath kilometres of ice, hydrothermal vents could provide the ingredients and energy life needs: water, warmth, minerals, and time. The surface above, meanwhile, acts like a protective roof, shielding that hidden ocean from cosmic radiation. It's a world turned inside out, sterile on the outside, potentially fertile within. Titan, Saturn's largest moon, offers a fascinating counterpoint. Its landscape is carved not by water but by liquid hydrocarbons, primarily methane and ethane, flowing through channels, pooling in lakes and forming seas. The physics is eerily familiar. Rain falls, rivers run, and evaporation feeds clouds, creating a full-fledged weather cycle. But the temperatures are far too cold for water to behave as a liquid. Instead, methane takes water's role, shaping valleys and beaches in slow motion at almost 200 degrees below 0 Celsius. The chemistry of Titan's seas is entirely alien, yet the resemblance to Earth's hydrological rhythm is unmistakable. Its dunes are sculpted by hydrocarbon sand, its atmosphere thick with nitrogen and organic haze. In this world, methane plays the part of water, and water itself exists only as hard rock. Scientists speculate that beneath Titan's crust, there may still be a hidden layer of liquid water mixed with ammonia, kept unfrozen by pressure and antifreeze chemistry? If so, Titan could host two oceans, one of methane at the surface and one of water far below. It's a reminder that while the ingredients of life might differ, the rules of physics stay the same. Further out and larger still are Jupiter's other icy moons, Ganymede and Callisto. Both are ancient, battered worlds, their surfaces scarred by billions of years of impacts. Yet beneath their frozen exteriors lie deep internal oceans, likely sandwiched between layers of ice, a sandwich model that might seem improbable until you consider the immense pressures involved. In these conditions, ice behaves strangely. It can form several distinct crystalline phases, some denser than liquid water. As a result, liquid layers can exist trapped between high-pressure ice below and regular ice above, sealed off from both space and rock. Ganymede, the largest moon in the solar system, even has its own magnetic field, a hint that its ocean may interact with a metallic core. That interaction could create subtle variations in the magnetic field detectable from orbit, which future missions like the European Space Agency's JUICE spacecraft aim to measure. Callisto, farther from Jupiter's heat, may have an ocean too, though colder and less active. If confirmed, it would mean that nearly every large icy moon in the outer solar system harbours liquid water in some form. The region once dismissed as frozen wilderness now appears to be an archipelago of hidden seas. Each of these moons tells the same quiet truth. Warmth isn't only about sunlight. Tidal forces, radioactive decay, and internal chemistry can create pockets of habitability in the coldest reaches of space. Beneath kilometers of ice, where light never reaches, heat still flows, and liquid still moves. It's a kind of cosmic irony. Worlds that look utterly frozen may, in fact, be more geologically and chemically alive than many rocky planets bathed in sunlight. The implications stretch beyond science. If life can exist, or even just persist in these buried oceans, it changes how we think about the universe. It suggests that life doesn't need a blue sky or an open sea. It might begin in darkness, feeding on chemical gradients instead of sunlight, exchanging energy in reactions too slow for our impatient senses. A biosphere beneath the ice would be silent, invisible, and profoundly enduring. Life that hums rather than shines. It's humbling to imagine the diversity of such possibilities. Picture a world where an ocean surface is sealed beneath ice kilometers thick, the roof glowing faintly from auroral light above. Below, in the endless dark, water currents stir over mineral ridges, dissolving elements and forming molecules that drift and combine. There's no need for continents or air, just chemistry, motion, and time. The kind of life that might emerge there would never know stars or sky, only the slow pulse of warmth from the world's interior. Perhaps that's what makes these frozen moons so haunting. They remind us that life doesn't need to resemble us, or even share our sunlight. It just needs a place to happen, a space where liquid, energy, and patience intersect. Europa's fractures, Enceladus's plumes, Titan's methane lakes, Ganymede's layered seas, each one a variation on the same ancient theme: water, in all its guises, refusing to rest. If you could stand on the surface of one of these moons, the scene would be stark, a landscape of endless white under a dim, distant sun. The ice would creak softly beneath your boots, and the horizon would blur into darkness. Yet deep below, an ocean might be moving, whispering in slow tides. Somewhere in that hidden sea, chemistry could be weaving quiet patterns of complexity, waiting for discovery. In the frozen silence of those alien worlds, the universe's oldest experiment continues, liquid persistence beneath the coldest roofs imaginable. Water isn't confined to planets, moons, or comets. It is a traveller of the cosmos, woven into the chemistry of stars themselves. Across the galaxy, water molecules drift through clouds of gas and dust, forming, freezing, and evaporating in cycles as old as time. Even in places where temperatures plunge hundreds of degrees below zero or rise to thousands, traces of water endure. It is, in a quiet way, one of the universe's most faithful companions, appearing wherever physics allows and chemistry dares. In the earlier stages of star formation, vast clouds of hydrogen, helium, and dust begin to collapse under gravity. As the cloud condenses, the core grows denser and hotter, igniting nuclear fusion. Around that newborn star, the protostar, envelopes of gas and dust swirl, forming disks that may one day become planets. Within these cocoons, water takes shape in abundance. Observations show that even before a star fully ignites, water vapor fills the warm regions of its disk, while ice coats grains farther out where it's cold. Astronomers detect this cosmic water through one of the universe's strangest natural amplifiers, masers. The term stands for microwave amplification by stimulated emission of radiation, and water molecules are particularly good at producing it. Under the right conditions of temperature and density, water emits powerful microwave signals, creating natural radio beacons that can be detected from thousands of light years away. These water masers appear in star-forming regions, around dying stars, and even in the swirling disks of supermassive black holes. To radio telescopes, they look like pinpoints of brightness, marking places where water vapor amplifies starlight into something the cosmos itself seems to whisper through. Within molecular clouds, the nurseries of stars, water exists mostly as ice coating the surfaces of dust grains. These grains, no larger than smoke particles, act as tiny laboratories. On their surfaces, hydrogen and oxygen atoms meet, react, and freeze, building up mantles of water, methanol, carbon dioxide, and other simple molecules. These icy coatings are not static. They participate in a grand freeze and release cycle that defines interstellar chemistry. When a nearby star flares or a shockwave passes through, the grains warm just enough to release their icy cargo as vapor. Later, as the region cools again, the molecules freeze back onto other grains, locking fragments of chemistry into solid form. Over millions of years, these cycles of freezing and evaporation enrich the interstellar medium with complex organics. Some of the ices even form amino acid precursors, the same kinds of molecules found in meteorites and comets. In this way, the chemistry of water becomes the chemistry of potential life long before any planet exists to host it. The universe, it seems, has been running the same quiet experiment everywhere. Combine hydrogen, oxygen, carbon, and time, and see what emerges. Eventually, parts of those clouds condense into protoplanetary disks, flattened rings of dust and gas orbiting young stars. Within them, temperature dictates form. Close to the star, water exists as vapor. Farther out, beyond what astronomers call the snow line, it freezes onto dust grains. That boundary is crucial. Inside the snow line, rocky planets form from dry materials. Beyond it, icy bodies coalesce, rich in water and other volatiles. The difference explains why Earth sits between two worlds, the parched inner planets and the frozen outer ones. Our own oceans most likely came later, delivered by icy comets and asteroids that wandered inward, carrying the memory of those outer regions. Comets are often called the time capsules of the solar system. They are relics from the cold outskirts, formed from the same mixture of dust and ice that built the planets, then locked in deep freeze for billions of years. When they approach the sun, heat awakens them. Their ices sublimate, turning directly into vapor, creating glowing tails that reveal their contents. By studying the light from those tails, scientists can measure the isotopic ratios of hydrogen within the comet's water. Comparing those ratios to Earth's oceans allows them to trace our planet's heritage. Some comets, especially those from the outer regions, match surprisingly well. It suggests that the water you drink might once have drifted between the stars, frozen into a grain of interstellar frost long before Earth existed. Even now, comets and icy asteroids continue to deliver water throughout the solar system. Impacts have likely refreshed Mars's polar ice caps, supplied Europa's subsurface ocean with salts, and even carried organics to Titan's hazy surface. They act as cosmic couriers, spreading the raw ingredients of chemistry wherever gravity permits. In this way, water's story is not linear but circular, a perpetual migration from vapor to ice, from dust grain to planet, and sometimes back again. Astronomers have found water almost everywhere they've looked. It swirls in the atmospheres of gas giants, freezes on the surfaces of dwarf planets, and lingers in the thin exospheres of Mercury and the Moon. Even the sunlit rings of Saturn contain ice particles sparkling like powdered mirrors. Beyond our solar system, observations reveal that exoplanets orbiting other stars also carry water in their clouds or on their surfaces. Each new discovery suggests that water is not a rare luxury of Earth, but a universal tendency, a molecular pattern the cosmos seems to favour. What's most remarkable is how this universal substance connects scales of time and space. The same water vapour that glows in masses light years away obeys the same physics as the droplet on a leaf. The same ice that coats distant dust grains follows the same rules as the frost on your window. From molecular clouds to mountain streams, water is both ancient and immediate, the link between starlight and life. Picture the moment when a star first ignites. Around it, a cocoon of dust and ice swirls, heated from within. Some of the ices sublimate, releasing water vapour that catches the newborn starlight, scattering it into shimmering halos. Farther out, grains remain frozen, their crystalline shells glinting faintly in the darkness. Each grain holds the potential for oceans yet unborn, for clouds and rain on worlds that do not yet exist. The entire scene glows with a cold radiance, light reflected from frost waiting patiently for morning. That image, starlight caught in ice, captures the essence of cosmic chemistry. Water doesn't just appear when life arrives, it precedes it, shaping the conditions that make life possible. It threads through the story of the universe like a clear, continuous river, from the first collapsing cloud to the glass of liquid you might hold now. Somewhere, in the quiet reaches between stars, that same chemistry continues. Vapor freezing, ice melting, light reflecting. The universe is full of oceans still waiting to melt. Water is one of the simplest molecules in the universe, yet it shapes almost everything we know. From its first appearance in the early cosmos to the glass of water beside you now, it has been at the centre of chemistry, geology, biology, and even astronomy. Its bent shape and uneven charge give it remarkable properties, allowing it to stick, dissolve, expand, and store heat in ways few other substances can. Those traits built the landscapes around us. The rivers that carved valleys, the glaciers that sculpted continents, and the clouds that carry rain across the world. Inside living things, water does just as much. It forms the background for every reaction inside cells, helps proteins fold, and moves nutrients through the body. It regulates temperature, carries oxygen and minerals, and keeps every system in balance. Even our thoughts depend on it. The brain is mostly water, and without it, concentration and calm disappear fast. Across the planet, wherever liquid water exists, life follows. It has been the same pattern for billions of years. Beyond Earth, water continues the story. We've found it frozen on moons, buried under Mars, and drifting as vapour in the atmospheres of distant planets. It forms icy shells around comets and coats dust grains in the clouds where stars are born. Those frozen particles help new solar systems form and deliver the ingredients for life to young planets. In a real sense, the water in our oceans may have begun between the stars. If you trace it all the way through, from molecule to mountain stream, from cell to cloud, it's clear that water isn't just a feature of life. It's one of the reasons life can exist at all. It connects the smallest chemical reaction to the largest planetary process. It's the same liquid falling as rain, circulating in your bloodstream, and glinting in the light around distant suns. Take a moment to breathe quietly, in and out, the same rhythm that drives waves and rain cycles. Every breath releases moisture into the air, adding a small piece of yourself to the water around you. That connection is steady, familiar, and constant, whether you're awake or asleep. Thank you for listening and for taking the time to slow down and wonder about something so ordinary yet so extraordinary. As you settle into rest, remember that water will keep moving, cycling and watching over the world, calm, dependable and always there.